Imagine a world so distant, so shrouded in cold and shadow, that its very existence feels like a whisper at the edge of the cosmic void. This is Varuna, a mysterious dwarf planet residing deep within the Kuiper Belt, a vast, icy realm far beyond the orbit of Neptune. For decades, scientists have peered through the most powerful telescopes, trying to decipher the secrets of this enigmatic object, only to find themselves confronted with a staggering number of puzzles. Varuna is not just another icy rock, it's a cosmic enigma wrapped in 30 layers of unexplained mysteries, each one more baffling than the last. These aren't just minor scientific questions, they are fundamental challenges to our current understanding of how planetary bodies form and evolve in the frigid outer reaches of our solar system. The sheer number of unresolved questions surrounding Varuna is unprecedented for an object of its size and location, suggesting that this distant world holds keys to unlocking profound truths about the early solar system. Perhaps the most compelling aspect of Varuna's mysteries is their potential to reshape our entire perspective on the Kuiper Belt itself. We tend to think of this region as a static collection of icy remnants, but Varuna's peculiarities hint at dynamic, perhaps even violent, processes we've yet to comprehend. The mysteries of Varuna aren't confined to just a few oddities. They range from its unusually rapid rotation, spinning like some kind of cosmic top, to strange variations in its brightness that defy simple explanations. There are questions about its composition. Is it primarily ice, or is something else hidden beneath its frozen surface? Its orbit, while broadly within the Kuiper Belt, has subtle characteristics that puzzle orbital dynamicists, hinting at gravitational influences from undetected objects or perhaps even deviations from our standard models of celestial mechanics. Every new observation seems to add another layer of complexity, pushing us further into the unknown. Think about the sheer challenge of studying something so small and distant. Light takes hours to reach us from Varuna, and even the largest telescopes see it as little more than a faint speck. Yet, within that speck lies a universe of unanswered questions, each one a thread in a larger tapestry of cosmic mystery. The scientific community is buzzing with theories, hypotheses ranging from the plausible to the truly speculative. Could Varuna have collided with another object in the relatively recent past? Is its rapid spin a remnant of some ancient energetic event? Or are we witnessing entirely new phenomena, processes at play in the outer solar system that our current theories simply can't account for? As we embark on this journey into the heart of Varuna's 30 unexplained mysteries, prepare to have your understanding of the Kuiper Belt challenged and expanded. We'll explore the most compelling clues, the most puzzling observations, and the cutting-edge theories that scientists are developing to try and make sense of it all. This exploration is not just about a distant dwarf planet. It's about the very limits of our knowledge, the vastness of the cosmos, and the enduring human drive to understand the universe around us. Join me as we dive deep into the enigmas of Varuna, a world that proves even in our own cosmic backyard, there are still countless secrets waiting to be uncovered. Each of the 30 mysteries we will explore offers a tantalizing glimpse into the potential for groundbreaking discoveries, reminding us that the age of exploration is far from over. Get ready to be amazed, to be puzzled, and perhaps to see the Kuiper Belt in an entirely new light. So, let's kick off our dive into Varuna's 30 mysteries with perhaps the most striking one, its bizarre rotation speed. Most objects out in the Kuiper Belt, especially ones of Varuna's size, tend to spin relatively slowly, taking maybe 8 or 10 hours or even longer to complete a single rotation. It's a leisurely pace typical for bodies that formed billions of years ago and haven't experienced much significant upheaval since. But Varuna is a cosmic speed demon. It whips around in just over 3 hours. Think about that for a second. an object hundreds of miles across, spinning so fast it completes more than 7 rotations in a single Earth day. This is wildly out of line with what we expect, and it immediately flags Varuna as something unusual, something that didn't follow the standard script for Kuiper Belt formation. Scientists are scratching their heads trying to figure out how it got this way. One of the leading theories revolves around a massive impact. Imagine Varuna in its early days, perhaps spinning at a more typical rate when suddenly another significant object slams into it. This wouldn't have been a gentle nudge. We're talking about a high-energy collision, powerful enough to completely alter Varuna's rotational dynamics. This kind of impact could have imparted a tremendous amount of angular momentum, essentially giving Varuna a violent push that sent it spinning out of control. Evidence for such a collision might be visible if we could get a closer look, perhaps in the form of a slightly non-spherical shape or even a family of smaller fragments orbiting it, leftover debris from the impact. Unfortunately, from our distance, those details are impossible to discern. Another possibility, though perhaps less likely given its size, is that Varuna somehow accumulated material in a very specific way during its formation. Perhaps it pulled in dust and ice from a swirling disk in a manner that naturally led to this rapid spin, though the mechanics of how this could happen so effectively for such a large object are still debated. Then there's the idea that maybe, just maybe, Varuna isn't a single object at all, but 2 smaller bodies in very close orbit around each other, appearing as one from our vantage point. This binary scenario could potentially explain some aspects of its light curve variations, but it doesn't fully account for the overall rapid spin of the combined system. Whatever the cause, Varuna's rapid rotation is a major anomaly, a flashing red light telling us there's a story behind this dwarf planet that is far more dramatic than its quiet neighbors. It suggests a past filled with violent events, a history of cosmic bumper cars in the outer solar system that we're only just beginning to piece together. This single mysterious characteristic already tells us Varuna is different, hinting at larger, unknown processes at play billions of miles away. Following its bewildering spin, one of the next big head-scratchers when it comes to Varuna is its remarkably dark surface. Now, you might think that far out in the cold, everyone would look pretty similar, but that's just not the case in the Kuiper Belt. Many of Varuna's neighbors, objects like Eris or Makemake, are quite bright, covered in fresh ice that reflects a good amount of sunlight. They look almost pristine, like freshly fallen snow. Varuna, however, is different. It's significantly darker, absorbing much more of the sunlight that reaches it. This isn't just a small difference, it's a major contrast that tells us something fundamentally different is happening on Varuna's surface compared to many other large Kuiper Belt objects. So, why the gloom? Scientists have a few compelling ideas, but none are definitively proven. One leading hypothesis points to the presence of complex organic compounds on its surface. When icy materials are exposed to radiation from the sun and cosmic rays over billions of years, they can undergo chemical changes, forming dark, tar-like substances often called tholins. These same kinds of compounds are thought to give the surfaces of some asteroids and comets their dark, almost sooty appearance. If Varuna's surface is rich in these radiation-processed organics, it would naturally explain its low reflectivity. Think of it like leaving something sugary out in the sun. It slowly caramelizes and darkens. In space, radiation acts like the heat, slowly cooking the surface over eons. Another possibility is linked to a process called space weathering. This isn't about rain or wind like we have on Earth. Space weathering is the cumulative effect of bombardment by micrometeoroids, charged particles from the solar wind, and other forms of radiation. Over vast stretches of time, these impacts and particles can alter the optical properties of a surface, potentially darkening it or changing its color. It's like sandblasting a painted surface. Eventually, the underlying material is exposed, and in space, that exposure can lead to darkening. Perhaps Varuna's surface composition, combined with a unique history of bombardment or radiation exposure, has led to a more pronounced weathering effect than seen on brighter KBOs. There's also the idea that Varuna might have lost volatile ices from its surface over time. If ices like methane or nitrogen, which are highly reflective, have sublimated away, leaving behind a residue of darker, less volatile materials that could also contribute to its appearance. The challenge is figuring out which of these processes, or perhaps a combination of them, is the dominant factor. Without being able to analyze the surface composition directly, scientists rely on studying the light reflected by Varuna across different wavelengths. These spectral observations provide clues, but the data is faint and difficult to interpret from such a distance. The darkness of Varuna isn't just a cosmetic feature. It holds vital information about its history, its composition, and the processes that have shaped it over billions of years in the harsh environment of the Kuiper Belt. It's a puzzle piece that, once understood, could reveal a great deal about the diversity of objects in this distant region and the different evolutionary paths they've taken since the birth of our solar system. This dark surface stands in stark contrast to its rapid spin, suggesting a complex history with multiple distinct events leaving their mark on this enigmatic world. Beyond its rapid spin and dark surface lies yet another profound puzzle, the curious absence of a detectable atmosphere around Varuna. Now, you might think that way out in the deep freeze of the Kuiper Belt, no object would have an atmosphere, but that's not entirely true. We know dwarf planets like Pluto, which is roughly similar in size and composition to what we think Varuna might be, have thin, temporary atmospheres. Pluto's atmosphere is primarily nitrogen with traces of methane and carbon monoxide, and it expands when Pluto is closer to the Sun and largely freezes out when it's farther away. Given Varuna's estimated size and potential for hosting volatile elements like nitrogen or methane, it seems reasonable to expect at least a fleeting, tenuous atmosphere, especially if its orbit brings it close enough to the Sun at times to warm its surface. But repeated observations using sophisticated techniques designed to look for the subtle spectral signatures of atmospheric gases have come up empty. No sign of nitrogen, no sign of methane, nothing. It's as if Varuna is holding its breath, or perhaps it never had lungs in the first place. So what's going on here? Why would Varuna appear so devoid of atmosphere when a nearby neighbor like Pluto manages to cling onto one, even intermittently? One possibility is that Varuna simply lacks the necessary volatile materials in its composition. Maybe it formed from slightly different stuff than Pluto, with fewer ices that can easily sublimate into gas. This would suggest a difference in formation conditions or location within the early solar nebula. Another compelling explanation ties directly back to the rapid spin we discussed earlier. A rapidly rotating body experiences stronger centrifugal forces. While gravity is the primary force holding an atmosphere to a planet, a fast spin can make it easier for gas molecules to escape the gravitational pull, especially if those molecules are light and the temperature is even slightly elevated. The faster Varuna spins, the more challenging it is for any trace atmosphere to remain bound. This rapid rotation could be acting like a cosmic fan, blowing away any gases that manage to sublimate from the surface before they can accumulate into a detectable atmosphere. Think of it like trying to hold onto a handful of sand while spinning rapidly. The faster you spin, the harder it is to retain the sand. For Varuna, the sand is atmospheric gas, and the rapid spin is making retention incredibly difficult. Then there's the idea of surface conditions. Even if Varuna has volatile ices beneath its dark surface, the properties of that surface, perhaps its darkness absorbing more heat, or its texture affecting how gases escape, could influence atmospheric retention. If the surface is particularly porous, for example, gases might permeate into the subsurface rather than forming a stable layer above it. Another factor could be Varuna's orbital path. While it's in the Kuiper Belt, slight differences in its closest approach to the Sun compared to Pluto could mean it simply never gets warm enough for significant sublimation to occur in the first place. Even small temperature differences can have a dramatic effect on how much ice turns into gas. Each of these potential explanations for the missing atmosphere brings with it a cascade of other questions. If it lacks volatiles, why? If its spin is the culprit, what does that tell us about its formation history? The absence of an atmosphere around Varuna is a significant piece of the puzzle, suggesting that despite appearances, the conditions and processes shaping these distant dwarf planets can be remarkably diverse even among apparently similar objects. It's a stark reminder that our understanding of the Kuiper Belt is still very much in development. Adding to the long list of Varuna's peculiarities is the surprising possibility that it might not be perfectly round, the way we usually picture dwarf planets. While gravity tends to pull larger celestial bodies into a spherical shape, observations of Varuna hint at something different. The way its brightness changes as it rotates, known as its light curve, doesn't quite fit the pattern of a perfectly spherical object. If Varuna were a perfect ball, its brightness would remain relatively constant as it spins, assuming its surface has uniform reflectivity. But Varuna's light curve shows more significant variations than expected for a sphere, suggesting that we are seeing different amounts of surface area, or perhaps areas with different reflectivity as it rotates. This kind of pronounced variation in brightness is often indicative of an irregularly shaped object. Scientists are debating exactly what kind of irregular shape this might be. Is Varuna elongated like a cosmic potato or cigar, or is it flattened at the poles like a slightly squashed ball? Both shapes would lead to variations in the amount of light reflected towards us as the object spins. An elongated shape would show more dramatic changes in brightness as its long axis rotates into and out of view, while a flattened shape might show more subtle but still detectable variations. The question then becomes, what forces could have molded Varuna into such a non-spherical form? One of the most likely culprits, again, relates back to that incredibly rapid rotation. When an object spins very quickly, the centrifugal force is strongest around its equator. This force acts outwards, counteracting the inward pull of gravity. On a rapidly spinning body, this can cause the equatorial regions to bulge outwards while the poles become flattened. Think of how a ball of dough tends to spread out when you spin it on a table. For Varuna, its 3-hour rotation period is so fast that the centrifugal forces could be significant enough to overcome gravity's pull towards a perfect sphere, especially if the object isn't uniformly dense. If the rapid spin is the primary cause, it would suggest that the shape we observe is a direct consequence of its current rotation rate, a kind of equilibrium shape for a body spinning that fast. However, it's also possible that the unusual shape is a remnant of a past event, perhaps the same giant impact theorized to have caused its rapid spin. A violent collision could have left Varuna permanently deformed, its shape frozen in time after the energy of the impact dissipated. This deformation could have been a direct result of the collision itself, or it could be linked to fragmentation or internal changes caused by the impact. Distinguishing between these possibilities is difficult with current data. If the shape is purely due to rotational flattening, it tells us about the balance between gravity and centrifugal force on a rapidly spinning dwarf planet. If it's a result of an impact, it provides further evidence for a chaotic and violent past for Varuna. The strange, perhaps non-spherical shape of Varuna adds another layer to its enigmatic nature. It's a visual clue, albeit a faint one, that this isn't a typical Kuiper Belt resident. It suggests dynamic processes at play, whether ongoing forces like rapid rotation or echoes of ancient, powerful events. This mystery of its shape is intertwined with its spin and its history, each puzzle piece seemingly connected to the others in a complex cosmic dance. Future observations, perhaps by space telescopes with enhanced resolution or even a dedicated mission, will be crucial to precisely determine Varuna's shape and unlock this particular secret, which could provide vital clues about its internal structure and formation history. Adding another layer to Varuna's complex portrait are the hints of mysterious bright spots scattered across its otherwise dark surface. Remember how we talked about Varuna being unusually dark, possibly due to radiation-processed organics? Well, observations of its light curve and, in some cases, extremely challenging spectral data suggest that this darkness isn't entirely uniform. There appear to be patches or regions on Varuna that are significantly brighter than the surrounding terrain. These aren't just subtle differences. The contrast is enough to be detected even from billions of miles away, adding another significant anomaly to its profile. What could cause these islands of brightness on a predominantly dark world? One of the most compelling explanations points to deposits of fresh ice. While much of Varuna's surface may be covered in dark, weathered material, these bright spots could be areas where fresh, relatively unaltered ice is exposed. This ice could be water ice or perhaps more volatile ices like methane or nitrogen that haven't been fully processed by solar radiation and cosmic rays. But how would fresh ice appear on the surface of a world that's been bombarded by radiation for billions of years? This is where things get really interesting, pointing towards potential geological activity on Varuna, which is surprising for such a distant, presumably cold object. One possibility is cryovolcanism, essentially ice volcanoes. Instead of erupting molten rock like volcanoes on Earth, cryovolcanoes erupt a mixture of water, ammonia, methane, or other volatile compounds that are liquid at extremely low temperatures. If Varuna has an active interior, perhaps heated by tidal forces from an unseen companion or residual heat from its formation, this internal activity could be pushing these icy materials up to the surface. When the icy mixture reaches the frigid vacuum of space, the volatile components would rapidly freeze, creating a patch of fresh, reflective ice. These bright spots could be indicators of recent or even ongoing cryovolcanic eruptions. Think of it like finding patches of fresh snow in an otherwise dusty landscape. It suggests a recent deposition event. Another possibility for these bright spots is relatively recent impact. If a small meteoroid or a larger object impacted Varuna, it could have excavated material from beneath the dark, weathered surface, bringing fresher, brighter ice from deeper layers to the top. The impact site itself and the debris ejected from it could appear brighter for a time until space weathering darkens the newly exposed material. This would suggest a history of impacts, which is certainly plausible for any object in the crowded Kuiper Belt. However, the apparent distribution and persistence of these bright spots over time might favor a process of continuous renewal, making cryovolcanism a very intriguing, albeit speculative, explanation. There's also the idea that these bright spots could be areas where volatile ices that had sublimated into a temporary atmosphere have refrozen back onto the surface, though this would likely require specific temperature and pressure conditions that are hard to imagine on Varuna given the lack of a detectable atmosphere. The presence of these bright spots challenges the idea of Varuna as a static, unchanging body. They hint at dynamic processes, whether internal geological activity or external bombardment, that are actively shaping its surface. Understanding the nature of these bright regions is crucial for piecing together Varuna's history and composition. Are they evidence of cryovolcanoes making Varuna a surprisingly active world? Are they impact sites, indicators of its violent past, or are they something else entirely, a process unique to this mysterious dwarf planet? Each bright speck on Varuna's dark canvas tells a potential story of activity and change billions of miles away, adding another layer to its 30 unexplained mysteries and pushing the boundaries of our understanding of the outer solar system. Moving from the physical oddities of Varuna to something a little more cosmic, let's talk about the name itself. It's mystery number 6. Why did astronomers choose the name Varuna for this particular dwarf planet? Unlike many other Kuiper Belt objects that were given names from Greek or Roman mythology, Varuna draws its name from a completely different and fascinating source, Hindu mythology. Varuna is one of the most ancient and significant deities in the Vedic tradition, revered as the god of the cosmic ocean, water, justice, and the celestial realm. He is often depicted as upholding the cosmic order, known as Rita, and is associated with the vastness and mystery of the waters both on earth and in the heavens. So, out of all the possible names, all the pantheons and mythologies available, why did the International Astronomical Union, the body responsible for naming celestial objects, settle on Varuna for this distant, icy rock? The official reason given by the IU's naming committee is that Kuiper Belt objects are often named after mythological beings associated with creation, water, or the underworld. While Varuna might not be strictly an underworld deity in the traditional sense, his connection to the cosmic ocean and his role in maintaining universal order certainly fit the theme of distant, perhaps primordial realms. His association with water is also very relevant, given that Varuna is an icy world, likely composed of vast amounts of frozen water. However, the name feels particularly apt for a world that is so mysterious and challenging to understand. The cosmic ocean that Varuna presides over in Hindu mythology is vast, deep, and full of hidden currents and unknowable secrets, much like the Kuiper Belt itself, and much like the dwarf planet named after him. There's a sense of immense, unexplored depths, which perfectly mirrors the scientific uncertainty surrounding Varuna. Contrast this with the names of other prominent Kuiper Belt objects. Pluto, of course, is named after the Roman god of the underworld. Eris, a dwarf planet even more massive than Pluto, is named after the Greek goddess of discord and strife, a nod to the scientific controversy its discovery caused regarding what constitutes a planet. Makemake is named after the Rapa Nui creator god, fitting the theme of creation. Haumea is named after the Hawaiian goddess of fertility and childbirth, with its moons named after her daughters, reflecting the object's unusual shape and rapid rotation which is thought to have spun off these moons. Varuna's name stands out slightly from this more common Western mythological trend, drawing from a rich, ancient tradition from the Indian subcontinent. This choice adds another layer of intrigue. Was it simply because the name fit the general criteria of water/creation/underworld deities, or was there a recognition that this object, with its multitude of mysteries, evoked a sense of profound, ancient cosmic power and unknowable depth, much like the deity himself? The name itself seems to beckon us to look deeper, to acknowledge the mysteries that lie within this distant cosmic ocean. It's a subtle reminder that our exploration of the universe connects us to ancient human quests for understanding the cosmos, drawing inspiration from cultures and stories across the globe. The choice of Varuna wasn't arbitrary. It was a deliberate selection that reflects the deep, enigmatic nature of this dwarf planet and its place within the vast, mysterious Kuiper Belt. It suggests that the challenges Varuna presents are not merely scientific, but perhaps touch on something more fundamental about our place in a universe governed by forces we still only dimly perceive, much like the cosmic order Varuna is said to uphold. After pondering the intriguing choice of naming this mysterious world after the cosmic ocean deity, we encounter mystery number 7, a perplexing puzzle concerning Varuna's very substance, its baffling density. Scientists have attempted to calculate Varuna's density based on its estimated size and mass, which in turn is inferred from its brightness and orbital characteristics. However, the numbers just don't add up in a straightforward way. the calculated density for Varuna appears to be significantly lower than what you would typically expect for a solid, icy body of its size. If Varuna were a compact ball of rock and ice, similar to other dwarf planets we've studied more closely, its density should fall within a certain range. But Varuna seems to fall below that expected range. This discrepancy presents several intriguing possibilities, each of which challenges our assumptions about this distant world. One compelling explanation is that Varuna isn't as solid as it appears. It might be quite a porous object. Imagine a giant cosmic sponge full of empty spaces or voids within its structure. If Varuna has a significant internal porosity, meaning there are lots of gaps or empty pockets within its rocky and icy composition, its overall density would be lower than if it were packed solid. These voids could be a remnant of its formation process, perhaps as dust and ice particles accreted billions of years ago to form Varuna. They didn't settle into a tightly packed structure, leaving behind a significant amount of empty space. This is especially plausible if the materials came together relatively gently in the early stages. Another way to think about it is like a pile of gravel versus a solid rock. The gravel takes up more volume for the same amount of material because of the spaces between the pieces. Varuna might be more like a giant pile of icy, rocky gravel. Another possibility is that these aren't just microscopic pores but larger, hidden voids within the dwarf planet. Could there be cavernous spaces deep within Varuna, large internal cavities that reduce its average density? This is a more speculative idea, but not entirely out of the realm of possibility, especially if some internal process like partial melting and refreezing created these spaces. However, without seismic data or a closer look, detecting such internal voids remains purely theoretical. A third explanation for the low calculated density lies in the possibility of an unusual composition. Perhaps Varuna isn't made of the typical mix of rock and ice we assume for Kuiper Belt objects. Could it contain a much higher proportion of very light elements or compounds? While ice itself is relatively low in density compared to rock, a higher than expected ice-to-rock ratio could contribute to a lower overall density. Or perhaps there are significant amounts of other, less dense frozen volatiles present, like nitrogen or methane ice, that are distributed throughout its interior, further reducing the average density. The challenge here is that our understanding of the composition of objects forming so far from the Sun is still evolving, and Varuna could hold clues to variations in the primordial building blocks available in different parts of the early solar system. Could the same giant impact that may have caused Varuna's rapid spin also be responsible for its puzzling density? A high-energy collision could have fragmented the object internally, creating a more porous structure or even blowing out lighter materials. Or perhaps the impact caused some internal rearrangement that resulted in large voids. The low-density calculation for Varuna is more than just a numerical curiosity. It's a critical piece of information that speaks to its internal structure, its composition, and its history. Is it a porous relic of formation? Does it hide vast internal spaces? Or is it made of materials we didn't expect? Each answer fundamentally changes our picture of this distant world and provides further evidence that Varuna is following its own unique evolutionary path in the frigid outer solar system. Adding climate to the confusion, we arrive at mystery number 8, the perplexing enigma of Varuna's surface temperature. Based on its distance from the Sun and its general characteristics, scientists can build models to predict how warm or, more accurately, how cold its surface should be. These models take into account factors like how much sunlight reaches Varuna and how reflective its surface is. But when actual telescopic observations designed to measure Varuna's thermal emission are compared to these predictions, there's a noticeable discrepancy. Varuna appears to be colder than the models suggest it should be. It's like putting a tray of ice cream in a freezer set to a certain temperature and finding it surprisingly colder than expected. This seemingly small difference in temperature holds significant implications for understanding Varuna's surface and subsurface composition, and even its potential geological activity. Several factors could contribute to this colder than predicted state. One key element is the albedo effect, basically how reflective Varuna's surface is. Remember how we discussed its unusually dark surface in Mystery Number 5. A darker surface absorbs more sunlight, which should, in theory, make it warmer than a brighter, more reflective surface. However, if those bright spots we talked about are more prevalent or more reflective than current observations suggest, they could be increasing the overall albedo, causing Varuna to absorb less total sunlight and thus appear colder. It's a delicate balance. The darkness should warm it, but if there are significant patches of brightness, they could be acting like tiny mirrors, bouncing away more heat than expected. This means the distribution and reflectivity of those bright spots are much more important than just a visual curiosity. They directly impact Varuna's energy balance. Another possibility is that our understanding of the thermal properties of the materials on Varuna's surface is incomplete. Different types of ice and rock radiate heat differently. If Varuna's surface is covered in a mix of materials whose thermal properties are not well represented in our current models, it could lead to an inaccurate temperature prediction. For example, a surface layer with very low thermal conductivity would insulate the interior, keeping the surface colder but potentially trapping heat below. Then there's the intriguing, albeit speculative, idea of internal heat discrepancies. While distant dwarf planets are generally thought to have cooled significantly since their formation, could Varuna be generating less internal heat than expected for an object of its size? Or perhaps that internal heat is being lost more efficiently than anticipated, radiating away into space rather than warming the surface. This could relate back to its potentially porous structure discussed in Mystery Number 7. A porous interior might allow heat to escape more easily. Conversely, it could mean Varuna formed with very little radioactive material, a common source of internal heating in planetary bodies, leading to a colder interior and surface. Or perhaps some of the energy from its rapid rotation is being dissipated in a way that somehow influences the surface temperature, though the mechanisms for this are not well understood. The mystery of Varuna's temperature is tightly linked to its other puzzles: its dark surface, its bright spots, its potential porosity, and its rapid spin. Each of these characteristics plays a role in how Varuna interacts with sunlight and how it retains or loses heat. The fact that our models are struggling to match the observed temperature suggests that there are fundamental aspects of Varuna's energy balance and surface composition that we don't yet grasp. It points to a need for more precise measurements and refined models that can account for the unique combination of traits found on this distant, cold, and mysterious world. Understanding why Varuna is colder than expected isn't just about getting a number right. It's about unlocking secrets about its surface properties, its internal structure, and its thermal evolution over billions of years in the deep freeze of the Kuiper Belt. Adding to Varuna's list of missing in action characteristics is Mystery Number 9, the surprising lack of any detected moons orbiting this distant dwarf planet. When we look at other large objects in the Kuiper Belt, especially those comparable in size to Varuna, finding moons is actually quite common. Pluto has 5 moons, Eris has 1, Haumea has 2. Even smaller KBOs often turn out to be binary systems, 2 objects of roughly equal size orbiting each other. It seems like having a satellite or 2 is practically the norm for the bigger players in this region. But despite considerable effort using powerful telescopes like Hubble, no moon has reliably been detected orbiting Varuna. This is puzzling. Why would Varuna seemingly be alone out there when its peers have companions? One obvious possibility is simply detection challenges. Varuna is incredibly far away and relatively faint. Any moon orbiting it would be even smaller and fainter, potentially lost in the glare of Varuna itself or simply too dim to be seen with current technology. We found moons around other KBOs because they were discovered during specific observation campaigns designed to look for them, often by noting subtle shifts in the object's position over time that indicate gravitational tugs from an unseen companion, or by carefully analyzing light curves for dips in brightness as a moon passes in front. It's like trying to spot a tiny firefly dancing around a distant flashlight in the dark. It requires very precise instruments and careful observation. It's entirely possible that Varuna does have one or more moons, but they are either too small, too dark, too close to Varuna, or too far away for our current telescopes to spot them. Future observations with even more advanced instruments, or perhaps using different detection techniques, might eventually reveal a lunar companion. However, the prolonged failure to detect one does raise questions. Could there be a physical reason for this moonless state? One theory relates to the rapid spin again, a recurring theme in Varuna's mysteries. Forming a stable moon requires a delicate balance of gravitational forces. If Varuna formed with a moon or captured one early in its history, its subsequent acceleration to its current rapid spin rate could have destabilized that moon's orbit, potentially causing it to crash back into Varuna, or more likely, be ejected from its gravitational embrace altogether. Imagine swinging a ball on a string. The faster you spin, the harder it is to keep the ball tethered. For Varuna and a potential moon, the rapid rotation could have provided the necessary centrifugal force to fling the moon away into interstellar space or send it on a collision course with another object. This scenario would suggest that if Varuna ever had a moon, it lost it relatively recently in cosmic terms, perhaps as a direct consequence of whatever event caused its rapid spin. Another possibility is that Varuna simply never formed with a moon and hasn't captured one since. Moons around KBOs are thought to form either from material thrown off during a giant impact like Pluto's moons, thought to be formed from a collision in its past, or through gravitational capture of passing objects. If Varuna avoided major moon-forming impacts since its rapid spin was acquired, and its gravitational pull isn't strong enough or its location isn't conducive to capturing passing KBOs into stable orbits, it might genuinely be a solitary world. The lack of a detected moon around Varuna isn't just a neutral observation, it's an anomaly that needs explaining. Is it a limitation of our technology, meaning the moons are there but hidden? Or does it tell us something fundamental about Varuna's history and the dynamic interactions it has undergone in the Kuiper Belt? The absence of evidence is not evidence of absence, but in Varuna's case, it's another piece of the puzzle, suggesting perhaps a more isolated or turbulent past than its moon-rich neighbors. The search for a Varunian moon continues, each new observation adding weight to the mystery of its apparent solitude in a crowded cosmic neighborhood. Stepping beyond its physical characteristics, we encounter mystery number 10, the subtle yet significant oddities within Varuna's orbit itself. While Varuna resides comfortably within the broad expanse of the Kuiper Belt, its specific path around the Sun isn't quite what you'd call standard for a classical Kuiper Belt object. Classical KBOs tend to follow relatively stable, near-circular orbits that haven't been significantly disturbed since the early days of the solar system. They orbit in a zone roughly 30 to 50 astronomical units from the Sun, largely avoiding strong gravitational interactions with the giant planets. Varuna, however, shows hints of a path that deviates slightly from this undisturbed norm. Its orbit is a bit more elliptical, meaning its distance from the Sun varies more significantly than the orbits of its more well-behaved neighbors. It also has a noticeable inclination, meaning its orbit is tilted relative to the main plane of the solar system where most of the planets reside. These orbital characteristics might seem minor, but in the precise, gravity-driven dance of the solar system, they are like fingerprints, indicating past experiences and gravitational encounters. The presence of both a higher eccentricity and a noticeable inclination suggests that Varuna's orbit hasn't been completely tranquil over the last 4.5 billion years. It looks less like a relic of smooth, early accretion and more like an object that has been nudged, pulled, or potentially even scattered at some point in its history. One leading explanation for these orbital oddities involves gravitational resonance. Resonance occurs when two orbiting bodies exert a regular, periodic gravitational influence on each other because their orbital periods are related by a simple ratio. For example, Pluto is in a 2-to-3 resonance with Neptune, meaning for every 2 orbits Pluto completes, Neptune completes 3. This gravitational relationship actually protects Pluto from being scattered away by Neptune. While Varuna doesn't appear to be in a major, stable resonance like Pluto's, its orbit might show signs of past, temporary, or weaker resonances with one of the giant planets, most likely Neptune. Even a temporary interaction could have been enough to pump up Varuna's eccentricity and inclination, kicking it out of a more classical orbit. Imagine a swing. If you push it at just the right moment during its arc, you can make it swing higher. Similarly, periodic gravitational tugs from a giant planet at certain points in Varuna's orbit could have gradually altered its path over millions of years. Another possibility points to past gravitational disturbances within the Kuiper Belt itself. The early solar system was likely a much more chaotic place. The giant planets, particularly Neptune, are thought to have migrated outwards from closer in orbits billions of years ago. This outward migration would have gravitationally stirred up the Kuiper Belt, scattering many objects, some inwards towards the Sun, potentially becoming comets, and others outwards to more distant and inclined orbits. Varuna's orbital characteristics could be a direct result of being caught up in this ancient scattering event, kicked into a more eccentric and inclined path by the moving gravitational field of a migrating giant planet. Its current orbit might be a stable configuration it settled into after that period of upheaval. The fact that Varuna exhibits these orbital eccentricities and inclinations, rather than residing in a neat, low inclination, near-circular orbit like some classical KBOs, links its present state to the dynamic history of the outer solar system. Its path tells a story of possible past interactions with giant planets or participation in the chaotic scattering events that shaped the Kuiper Belt into the structure we see today. Understanding the precise nature of Varuna's orbital parameters and whether they fit into known resonance patterns or scattering models is crucial for placing this object within the larger context of solar system evolution. It's a subtle mystery, but one that provides powerful clues about the forces that have relentlessly shaped this distant corner of our cosmic neighborhood over billions of years. Beyond its dark surface and bright spots, Varuna holds another visual secret, a subtle reddish hue that adds yet another layer to its enigmatic nature, making this mystery number 11. When astronomers analyze the sunlight reflected by Varuna using different color filters, they find it reflects more red light compared to bluer wavelengths. This reddish tint isn't unique to Varuna. Many objects in the outer solar system exhibit similar colors, but the specific shade and intensity of Varuna's redness are part of what make it a point of scientific debate. So, what gives Varuna its rusty blush? There are two primary contenders in the scientific ring, each with its own implications for Varuna's composition and history. The first theory points to the presence of tholins, those complex organic compounds we discussed earlier in relation to Varuna's dark surface. Tholins are formed when simple organic molecules like methane or ethane are zapped by high-energy radiation, such as ultraviolet light from the sun or cosmic rays. This radiation breaks apart the molecules, which then recombine into larger, more complex chains. These more complex molecules often have a reddish or brownish color. Think about the reddish haze around Saturn's moon Titan. That's thought to be due to tholins forming in its atmosphere and raining down onto its surface. If Varuna's surface ices, particularly those containing methane or other hydrocarbons, have been heavily irradiated over billions of years, a layer of reddish tholins could have built up, giving the dwarf planet its characteristic color. This theory aligns nicely with the idea of a dark surface, as tholins are typically very dark absorbers of light. The amount and specific type of tholins would determine the exact shade of red. The longer the exposure to radiation and the more abundant the source materials, the thicker and redder the tholin layer might become. The second major explanation for Varuna's color focuses more directly on the effects of irradiation on surface ices themselves, without necessarily requiring the formation of complex tholins as the sole culprit. This theory suggests that even pure or mixed ices, like water ice or various hydrocarbon ices, can undergo color changes when exposed to intense radiation over vast timescales. The radiation can create defects or alter the crystal structure of the ice, leading to changes in how it absorbs and reflects light, sometimes resulting in a reddish or brownish discoloration. This is similar to how some minerals change color when exposed to certain types of radiation. In this scenario, the reddish color isn't necessarily a separate organic layer, but rather the surface ice itself that has been literally sunburned or cosmic ray burned into a different shade. The debate between these two theories centers on the precise spectral signature of Varuna's reflected light. Different types and concentrations of tholins produce slightly different spectral patterns, as do different types of irradiated ices. By carefully analyzing the wavelengths of light reflected by Varuna, astronomers try to find a match with the spectral signatures of known materials, either laboratory-produced tholins or irradiated ice samples. The challenge is that spectral data from such a distant object is very faint and noisy, making it difficult to distinguish between subtle variations that could point definitively to one explanation over the other. Furthermore, it's possible that both processes are contributing to Varuna's color. A layer of tholins might be present, and the underlying or exposed ices might also be discolored by radiation. The intensity of the reddish color can also vary across the surface, possibly correlating with the dark and bright spots we discussed earlier, adding another layer of complexity to the puzzle. Are the bright spots areas of fresher, less reddened ice? Are the dark, reddish areas where tholins are most concentrated? The color of Varuna is more than just a visual detail. It's a chemical fingerprint left by billions of years of exposure to the harsh radiation environment of the outer solar system. Understanding whether its redness is primarily due to tholins or irradiated ice will provide crucial insights into the composition of its surface materials, the amount of radiation it has been exposed to, and the chemical processes that are actively shaping its outermost layers. It's a subtle mystery hidden in the light reflected from this distant world, waiting for more detailed spectral analysis to reveal its full story. Taking our investigation deeper into Varuna's surface properties brings us to mystery number 12, the enigma of its unexpectedly low albedo. Now, albedo is simply a measure of how much light a surface reflects. A surface with a high albedo, like fresh snow, reflects a lot of light and appears bright. A surface with a low albedo, like asphalt or charcoal, absorbs most of the light that hits it and appears dark. For a dwarf planet residing far from the sun, where temperatures are frigid and water ice is expected to be a major component, you might anticipate a relatively high albedo. Water ice is naturally very reflective, so you'd think Varuna would look brighter, more like a cosmic snowball. But as we touched on earlier, Varuna's albedo is significantly lower than what models predict for an object of its size and location with a significant amount of surface ice. This low reflectivity is one of its defining characteristics, making it dimmer than many other Kuiper Belt objects its size, and it ties directly back to the mysteries of its dark surface and reddish hue. So, why is Varuna so uniquely non-reflective? the primary suspect is the presence of those dark, complex organic materials we discussed, the tholins. If Varuna's surface is indeed coated in a significant layer of these radiation-processed hydrocarbons, they would act like a dark blanket, absorbing much of the incoming sunlight before it can bounce back towards our telescopes. Imagine scattering charcoal dust over a patch of snow. The snow would look much darker and reflect less light. The thicker or more widespread the tholin layer on Varuna, the lower its overall albedo will be. The intensity of the solar ultraviolet radiation and cosmic ray bombardment in the Kuiper Belt is high over billions of years, and if Varuna's original composition included a sufficient amount of simple hydrocarbons, the conditions are certainly right for the formation of significant tholin deposits. Another contributing factor could be the nature of the ice itself, even if it's primarily water ice. If the ice is mixed with other, less reflective materials, or if its physical structure is granular or porous, it won't be as reflective as pure, smooth ice. For instance, frost is more reflective than compacted ice. The way ice crystals form and are structured on Varuna's surface, influenced by temperature fluctuations and the history of impacts or potential cryovolcanism, could also play a role in its reflectivity. Furthermore, the process of space weathering itself, the constant bombardment by micrometeoroids and solar wind particles, can darken and roughen a surface over time, reducing its albedo. This is like sandblasting a smooth, reflective surface until it becomes dull and less able to bounce light back efficiently. The combined effects of radiation processing and micrometeoroid impacts could be particularly effective at reducing Varuna's albedo compared to other KBOs if its surface composition or geological history is different. The low albedo is a critical observational constraint for scientists trying to model Varuna. Any successful model of Varuna's surface must be able to reproduce this observed darkness. It strongly suggests that the outermost layers of Varuna are dominated by substances that are highly absorbent of visible light, pointing towards a surface composition distinct from brighter KBOs like Eris or Makemake. It implies a surface that has undergone significant alteration since its formation, whether through the slow accumulation of radiation-processed organics or the cumulative effects of space weathering. Understanding the precise reasons for Varuna's low albedo is essential for unlocking the secrets of its surface composition and the processes that have shaped it over cosmic time. It's a piece of the puzzle that, like its rapid spin and reddish color, points to a history and evolution that sets Varuna apart in the distant, icy reaches of our solar system. Following the mysteries of its surface properties, we arrive at mystery number 13, a puzzle about something that is missing from Varuna, the puzzling absence of a coma. Now you might be thinking, what's a coma? Isn't that something you fall into? In astronomy, a coma is the fuzzy cloud of gas and dust that surrounds the nucleus of a comet when it gets close enough to the sun to warm up. As the sun's heat causes the comet's ices to sublimate, turning directly into gas, that gas carries dust particles with it, creating the characteristic glowing envelope that makes comets visible and beautiful. Many objects in the Kuiper Belt are thought to be essentially dormant comets, reservoirs of ice waiting to be nudged into an orbit that brings them closer to the sun, at which point they would wake up and develop a coma and tail. Even some objects that reside beyond the Kuiper Belt, like the centaurs which orbit between Jupiter and Neptune, show comet-like activity, developing faint comae even though they don't have traditional comet orbits. These are often called active asteroids or comets in transition. Given that Varuna is an icy body residing in the frigid Kuiper Belt, and given its size, which suggests it holds onto its internal heat and volatiles better than smaller objects, you might expect to see some signs of cometary activity, especially if its orbit brings it even slightly closer to the sun at times. Perhaps not a spectacular, visible from Earth tail, but maybe a faint, tenuous coma detectable with sensitive instruments. Yet, observations of Varuna have consistently failed to turn up any evidence of such activity. No detectable outflow of gas, no surrounding cloud of dust. It appears stubbornly inert, a silent block of ice deep in space. Why would Varuna, seemingly composed of the same kind of icy materials as objects that do show cometary activity, remain completely dormant? One possibility ties directly back to its surface properties. If that dark, tholin-rich surface layer is very thick and insulating, it might be effectively preventing the underlying ices from feeling the sun's warmth, even when Varuna is at its closest point to the sun in its orbit. Think of the thick crust on a pie. It keeps the filling warm inside. Varuna's dark surface could be acting as a super insulating crust, preventing sublimation and thus preventing the formation of a coma. This would mean the dark surface isn't just cosmetic, it's playing a crucial role in suppressing cometary activity. Another potential explanation relates to the specific composition of Varuna's ices. Perhaps it simply lacks the highly volatile ices like frozen carbon monoxide or carbon dioxide that sublimate readily even at the extreme temperatures of the outer solar system. If its ices are primarily water ice, which requires significantly more heat to sublimate in a vacuum, it might not reach the necessary temperatures for activity given its distance from the sun. This would suggest a difference in the primordial materials available where Varuna formed compared to where more active KBOs or centaurs originated. There's also the idea that any volatile ices that were initially present closer to the surface were lost early in Varuna's history, perhaps during a period when its orbit was different or during the energetic event that caused its rapid spin. If all the easily sublimated materials have long since escaped, only less volatile substances would remain near the surface, leading to a lack of current activity. The absence of a coma around Varuna is a significant piece of observational data because it constrains our understanding of its surface temperature, the composition of its shallow subsurface, and the effectiveness of its dark, low-albedo surface as an insulator. It adds another layer to the mystery of why Varuna seems to defy some of the expected behaviors for icy bodies in its region. It's a silent world, offering no wispy breath of gas to tell us about its inner workings, forcing us to rely on other, more challenging observations to piece together its story. This missing coma isn't just an oversight, it's a piece of the puzzle that speaks to Varuna's unique thermal and compositional state, making it stand out even among the varied inhabitants of the distant Kuiper Belt. Adding another twist to its already convoluted profile, we arrive at mystery number 14, the puzzle of Varuna's potentially tilted rotation axis. Just like Earth is tilted on its axis, giving us seasons, other celestial bodies also have an axial tilt. This tilt determines which parts of the planet receive more direct sunlight at different points in its orbit. For Varuna, determining the exact orientation of its spin axis is incredibly difficult from our distance. It requires meticulous observations of how its brightness changes over time and how those changes correlate with our viewing angle as it orbits the sun. But the data we have suggests that Varuna's axis isn't neatly aligned. Preliminary analyses indicate its rotation axis is likely significantly tilted, perhaps even off-kilter in a way that is unusual for an object of its assumed characteristics. Why does a tilted axis matter? Well, it points to something substantial happening in Varuna's past. Unlike its rapid spin, which could be a result of ongoing forces or a singular event, a significant axial tilt is almost always the consequence of a major impact or a powerful gravitational interaction. Imagine a spinning top. If you just flick it gently, it spins upright. But if you hit it hard from the side, its axis of rotation will change dramatically and it will wobble erratically. Similarly, if Varuna experienced a violent collision with another large object early in its history, the sheer force of the impact could have fundamentally altered its rotational dynamics, knocking its spin axis significantly off its original orientation. This scenario aligns neatly with the theory that a giant impact also caused Varuna's rapid spin, and perhaps its non-spherical shape and even the potential lack of a moon. A single, powerful collision could potentially explain multiple mysteries simultaneously, providing a unifying event in Varuna's chaotic past. Another possibility is that Varuna's axial tilt was influenced by a strong gravitational interaction with a much larger body. Perhaps a close pass by one of the giant planets like Neptune, or even a close encounter with another massive Kuiper Belt object, could have exerted a tidal force strong enough to reorient Varuna's spin axis. This would require a very specific kind of encounter, one that transferred angular momentum without necessarily disrupting Varuna completely. While gravitational nudges can alter orbits, significantly tilting a rotation axis usually requires a much more powerful and precisely timed interaction. The degree of Varuna's suspected tilt is key here. If it's a relatively small tilt, it might be attributable to minor interactions or even a cumulative effect of smaller impacts over time. But if the tilt is substantial, leaning over by many tens of degrees, it strongly favors a single, large-scale event like a giant impact as the most likely cause. Determining the precise angle of Varuna's tilt remains a challenge, pushing the limits of observational astronomy. Future observations with even more sensitive instruments, potentially over multiple years to capture different viewing geometries as Varuna moves in its orbit, will be needed to refine our estimates of its axial orientation. But the current hints of a significant tilt add weight to the narrative of a dynamic and potentially violent past for this distant world. It's another piece of the puzzle that distinguishes Varuna from its more placid neighbors and suggests that key events shaped its evolution in ways we are only beginning to understand. Whether caused by a cosmic fender bender or a close gravitational dance, the mystery of Varuna's tilted axis points towards a history far more dramatic than its current quiet existence might suggest, further deepening the enigma of this rapid spinning, dark and solitary world. Following the possibility of a tilted axis which hints at past violence, we arrive at mystery number 15, the fundamental riddle of Varuna's age and origin. Is Varuna a primordial object, largely unchanged since the earliest days of our solar system, a relic formed directly from the swirling cloud of gas and dust billions of years ago? Or is it a fragment, a piece broken off from a much larger body during a catastrophic collision? The answer to this question profoundly impacts our understanding of not just Varuna, but the entire history of the Kuiper Belt. If Varuna is primordial, it represents a snapshot of the conditions and processes that existed in the outer solar system shortly after the Sun ignited. It would be like finding an untouched fossil, preserving information about the environment it formed in. Its composition, its internal structure, and even its initial spin rate would all be remnants of that early era. Studying a primordial Varuna would give us direct insights into the temperatures, pressures, and material distribution in the distant reaches of the solar nebula. We could compare its properties to models of accretion and planetesimal formation in cold environments, using Varuna as a test case for our theories about how the building blocks of planets came together far from the Sun's heat. However, several of Varuna's characteristics, particularly its rapid spin, non-spherical shape, and potential lack of moons, point strongly towards a disruptive event in its past, making the primordial scenario less straightforward. This leads to the second major possibility, that Varuna is a fragment. The idea here is that Varuna was once part of a much larger dwarf planet that was subsequently shattered by a massive impact billions of years ago. Such an impact could have broken the larger body into multiple pieces, one of which is the object we now call Varuna. This scenario could elegantly explain several of the mysteries we've already discussed. The rapid spin could be a result of the angular momentum imparted to the fragment during the collision. The non-spherical shape could be the irregular remnant of a broken body, unable to fully reshape itself into a sphere after the impact. The lack of moons could be because any pre-existing moons were destroyed or ejected during the impact, and the resulting fragments were too small or too energetic to retain satellites. Evidence for this kind of fragmentation event in the Kuiper Belt exists in the form of collisional families, groups of objects that share similar orbital characteristics, suggesting they originated from the same parent body. We see this in the Eris family, for example, where several smaller KBOs share orbits similar to Eris, believed to be fragments from an impact on Eris or its precursor. While Varuna's orbit doesn't clearly place it within a known collisional family, its unusual individual properties make a fragmentation origin highly plausible. How do scientists try to determine which scenario is more likely for Varuna? One method involves looking for evidence of surface age, albeit indirectly. On solid surfaces in the solar system, like planets or moons, the number of impact craters can give us a rough idea of how old the surface is. A heavily cratered surface is generally older, having accumulated more impacts over time, while a sparsely cratered surface suggests it is relatively young, perhaps having been resurfaced by geological activity or being a recently formed fragment. For Varuna, directly counting craters is impossible with current telescope resolution. However, astronomers can infer something about its surface history by analyzing the distribution of dark and bright patches. If the bright spots are indeed exposed fresh ice from recent impacts, their number and size distribution could potentially provide clues about the rate of bombardment Varuna has experienced, which in turn relates to the age of its surface. Dynamical models also play a crucial role. By simulating the orbits and interactions of objects in the early Kuiper Belt, scientists can test whether a primordial object like Varuna could have retained its characteristics, or whether its current orbit and spin are more consistent with being a fragment scattered from a larger body during a period of instability. Understanding whether Varuna is a primordial survivor or a fragmented remnant is critical for piecing together the history of the Kuiper Belt. It speaks to the frequency and intensity of collisions in this distant region, and the degree to which the original population of KBOs has been preserved versus fragmented over billions of years. Varuna's age is tangled up with its history of violence and its unique properties, making this question of origin one of the most fundamental mysteries surrounding this enigmatic dwarf planet. Following the question of Varuna's ancient origins, we move to mystery number 16, a puzzle that challenges our understanding of its interior, Varuna's apparent radio silence. Most celestial bodies, even those far from the Sun, emit some level of radio waves. These emissions can come from various sources, such as the interaction of a magnetic field with charged particles, or even thermal radiation from the interior. For Varuna, however, radio astronomical observations have revealed an unusually weak signal, or perhaps no detectable signal at all in the radio spectrum. It's remarkably quiet, even by the standards of distant, cold objects. This lack of radio emission is puzzling because many of the processes we might expect to be happening inside or around a dwarf planet like Varuna should produce some level of radio energy. For instance, if Varuna had a significant magnetic field, its interaction with the solar wind could potentially generate radio emissions, similar to how Jupiter's powerful magnetic field produces intense radio bursts. The absence of detectable radio waves could suggest that Varuna either has a very weak magnetic field or none at all. Creating a magnetic field typically requires a combination of a conductive fluid interior, like molten iron or a salty liquid, and a process called convection, where that fluid is in motion. Deep within a large object, radioactive decay can generate enough heat to keep some materials molten or in a fluid state for billions of years. If Varuna's interior lacks the necessary heat source, or if the materials within it are not sufficiently conductive, it might be unable to generate a magnetic field. Its potentially low density, which we discussed earlier, might also play a role. a less dense interior could mean less rocky material available for radioactive heating or less pressure to maintain fluid layers. Another possibility is that the expected sources of radio emission are simply not present or are suppressed on Varuna. Thermal radiation from even a very cold interior should produce some emission in the far radio wavelengths related to the object's temperature. The lack of a detectable thermal radio signal could imply an even colder interior than our models predict, or it might suggest that our assumptions about the composition or physical state of Varuna's interior are incorrect. Perhaps its interior is extremely homogeneous and solid, lacking the internal processes that typically generate detectable thermal noise. It could also be related to the distribution of radioactive elements within Varuna. If these heat-generating elements are concentrated near the surface or have decayed significantly, the interior might be surprisingly cold. Furthermore, interactions between Varuna and its environment, such as micrometeoroid impacts or even subtle gravitational influences from other objects, could theoretically generate some radio waves. The apparent silence suggests that these interactions might be minimal or that any resulting emissions are below our detection threshold. The mystery of Varuna's radio silence is closely tied to its invisible interior. It hints at the possibility of a stagnant, non-convective core, a low abundance of conductive materials, or a remarkably cold interior. It provides an indirect constraint on what might be happening beneath that dark, icy surface. Unlike visible light or infrared radiation, which primarily tell us about the surface, radio waves can sometimes penetrate deeper, offering glimpses into the subsurface. Varuna's quietness in this part of the spectrum suggests a lack of the kind of internal activity that we see or expect to see in other, perhaps more dynamic celestial bodies. Solving this mystery would require more sensitive radio telescopes or perhaps different observation techniques. It's a subtle puzzle hidden in the invisible waves emanating from this distant world, revealing its quiet interior just as its rapid spin screams of a violent past. The lack of radio chatter from Varuna is not just an absence of noise, it's a clue suggesting a potentially inert interior, a stark contrast to the energetic story told by its surface features and orbital path, adding another piece to the complex and often contradictory nature of this enigmatic dwarf planet. Moving from its surprising radio silence, we confront mystery number 17, a fundamental paradox about Varuna itself, reconciling the conflicting estimates of its size. You'd think determining how big something is would be one of the first and easiest things astronomers figure out, but for Varuna, even this basic characteristic is shrouded in uncertainty. We can't directly measure Varuna with a ruler. Our estimates of its diameter come from sophisticated observations and calculations, but different methods yield different answers, and those discrepancies are significant enough to cause scientific headaches. One primary way we estimate the size of a distant object like Varuna is by measuring the amount of sunlight it reflects back towards us. This is where its albedo comes into play. If we assume a certain surface reflectivity, or albedo, we can calculate how large the object must be to reflect the amount of light we observe. So, if we see a certain amount of light coming from Varuna, and we assume it's covered in bright, reflective ice high albedo, then it must be relatively small to produce that much reflected light. Conversely, if we assume its surface is very dark and absorbs most light low albedo, then it would need to be much larger to reflect the same amount of light we detect. The challenge here is that, as we've already discussed, Varuna's albedo is itself a mystery. Without knowing its true reflectivity, the size estimate based on reflected light is highly uncertain. It's a bit of a circular problem. To know its size, we need its albedo, and to fully understand its albedo, knowing its size is helpful for context. This is often called the albedo size degeneracy. If its albedo is on the higher side, maybe around 10 to 15%, its diameter might be on the lower end of estimates, perhaps around 600 kilometers. But if that surface is incredibly dark with an albedo closer to the low single digits, then Varuna would have to be considerably larger, possibly pushing towards 900 or even 1,000 kilometers in diameter, getting closer in size to dwarf planets like Ceres or even Pluto. The second main method for estimating Varuna's size relies on measuring the heat it emits, its thermal radiation. Every object that has a temperature above absolute zero radiates heat, and this radiation is strongest in the infrared part of the electromagnetic spectrum. Since Varuna is warmed by the sun, it emits thermal radiation. The amount of thermal radiation an object emits depends on its temperature and its surface area. If we can measure the thermal emission and estimate Varuna's temperature, which, as we saw, is also tricky, we can then calculate its size. A larger object will radiate more heat than a smaller one at the same temperature. The advantage of this method is that it's less dependent on the albedo of the visible surface. While surface properties do influence how efficiently heat is radiated, a factor called emissivity, which is generally less variable than albedo for these types of objects, the thermal measurement gives us a more direct handle on the physical surface area. Observations in the thermal infrared using telescopes like the Spitzer Space Telescope or the Herschel Space Observatory have provided crucial data here. However, these measurements are extremely challenging due to Varuna's vast distance and cold temperature, making its thermal signal very faint. The estimates derived from thermal emission tend to favor a larger size for Varuna, generally falling in the range of 800 to slightly over 900 kilometers, placing it among the larger known Kuiper Belt objects. This larger size estimate from thermal data seems to be in tension with the smaller size estimates that would result if Varuna had a higher albedo like some other icy bodies. The fact that the thermal measurements suggest a larger size when coupled with the observation of low reflected light strongly reinforces the conclusion that Varuna must have a very low albedo. If it was smaller, like the lower-end estimates from visible light might allow, if its albedo were higher, it wouldn't be emitting the amount of thermal radiation we observe. So the paradox isn't just about getting different numbers, it's about the numbers from one method, thermal, pushing us towards a conclusion larger size, therefore very low albedo, that deepens the mystery of the other property, albedo, and ties back into other puzzles like the reason for its dark surface. Reconciling these size estimates and using them to refine our understanding of Varuna's albedo and surface temperature is a critical step in building an accurate physical model of this distant world. It highlights the interconnectedness of Varuna's mysteries. Solving one often requires making progress on another, making the process both frustrating and incredibly compelling for the scientists involved. Beyond the confusing size estimates, we encounter mystery number 18, the perplexing lack of spectral evidence for certain common ices on Varuna's surface. When astronomers use spectroscopy, a technique that splits light into its component wavelengths, they are essentially looking for chemical fingerprints. Different materials absorb or reflect light at specific wavelengths, creating unique patterns in the spectrum. By analyzing these patterns in the light reflected from Varuna, scientists can try to identify the substances present on its surface. For an object in the Kuiper Belt, especially one of Varuna's size, we fully expect to see clear spectral signatures of common ices like water ice, and perhaps more volatile ices such as methane or nitrogen, which are abundant in this region. However, the spectral data from Varuna has been surprisingly ambiguous. While there are hints and debated interpretations, there is no definitive, strong spectral signature for water ice, which is thought to be a fundamental building block of cabios. Nor are there clear, unambiguous signs of methane or nitrogen ice. This lack of clear spectral features for expected materials is a significant puzzle. It's not that we see evidence of something completely alien. Rather, we're not seeing clear evidence of things we expect to be there based on our understanding of solar system formation and the composition of other KBOs. So why the spectral silence from these common ices? Several factors could be at play, many of them tying back to the mysteries we've already explored. One possibility is that the expected ice signatures are being masked or suppressed by the dominant surface material, that dark, reddish stuff likely tholins. If the tholin layer on Varuna's surface is thick enough, it could be absorbing or scattering the light in a way that smooths out or completely hides the spectral features of the underlying ices. Imagine trying to identify the color of paint underneath a thick layer of dark varnish. The varnish dominates the appearance and makes it hard to see what's underneath. Varuna's dark surface might be acting like that cosmic varnish, obscuring the spectral fingerprints of the underlying ice. Another explanation is related to the physical state of the ice. The spectral signature of ice can vary depending on its temperature and its crystal structure. Water ice, for instance, exists in different crystalline forms at different temperatures and pressures. If the ice on Varuna is in an unusual crystalline state due to its specific thermal history or internal conditions, its spectral signature might be different from the ones we typically look for, which are based on laboratory measurements of ice under more common conditions. Furthermore, if the ice is intimately mixed with other materials like rocky dust or organic compounds, it can alter the spectral signature, making it harder to identify. Think of trying to find the spectral signature of salt when it's mixed into a complex stew. The other ingredients can interfere with the measurement. It's also possible, though perhaps less likely for water ice, that the expected volatile ices like methane or nitrogen have mostly sublimated away from the very surface layers over billions of years, leaving behind less spectrally distinct materials. However, even if the volatile ices are gone, the lack of a clear water ice signature is still surprising unless that too is buried under a significant layer of other material. The faintness of Varuna itself being so distant makes obtaining high-quality spectral data extremely challenging. The signal is weak, and there's a lot of noise in the data, which can make it difficult to definitively identify subtle spectral features. Future observations with more powerful telescopes or instruments with higher spectral resolution will be crucial for confirming or refuting the presence of specific ices on Varuna's surface. The absence of clear spectral signatures for common ices isn't just a technical problem. It's a fundamental mystery about Varuna's composition. It suggests that either its surface is dominated by processing products like tholins to an extent we haven't fully appreciated, that the ice itself is in an unusual state, or that its composition is genuinely different from our expectations. This spectral silence leaves us wondering whether Varuna is truly made of the stuff we assume for KBOs, or if it holds secrets of unusual compositions forged in the deepest, coldest parts of the early solar system. It demands a deeper look, pushing the boundaries of our ability to analyze the chemistry of worlds billions of miles away. Adding to the confusion surrounding its composition, we encounter mystery number 19, the puzzle of Varuna's potential internal structure. While we can't see inside this distant world, its overall characteristics like its size, estimated density, and perhaps even its rotation provide clues to what lies beneath its surface. The question is, how are its rock and ice components distributed within Varuna? Is it a homogeneous mix like a cosmic fruitcake with rock and ice evenly distributed throughout? Or is it differentiated with heavier rocky materials sinking to the center and a lighter icy mantle surrounding a rocky core, similar to the structure of larger planets and some moons? If Varuna is differentiated, it would mean that at some point in its history, it was warm enough for the rocky and icy components to separate based on density. This process, called differentiation, requires a significant amount of internal heat. That heat could come from the energy of accretion, the process by which the object formed from colliding particles or from the decay of radioactive elements within the rocky material. For differentiation to occur in an object of Varuna's size, it would likely need to have retained enough internal heat from its formation, or have a sufficient abundance of radioactive isotopes to melt or significantly soften the interior enough for denser materials to sink. If Varuna is differentiated, it suggests it reached a certain threshold of size and internal temperature early in its history. This would place it in a category with other differentiated icy bodies like Pluto and possibly Eris, implying a similar process of internal evolution. However, if Varuna is largely undifferentiated, it would suggest that it never got warm enough or perhaps cooled too quickly for the rocky and icy components to separate. It would remain a more primitive, roughly equal mix of its constituent materials. An undifferentiated structure might be expected if Varuna formed relatively gently without a lot of accretional heating, or if it has a lower than average abundance of radioactive elements. Its potentially low density, discussed earlier, could also hint at an undifferentiated porous structure, as dense rocky material hasn't fully settled to a core. The rapid rotation adds another layer of complexity to this mystery. If Varuna is significantly differentiated with a dense core and an icy outer layer, its response to tidal forces from potential past close encounters or even its own rapid spin could be different than if it were a homogeneous object. The distribution of mass within the object affects its moment of inertia, which in turn influences how it spins and how its spin might have evolved. Trying to reconcile Varuna's rapid spin with potential differentiation scenarios is an ongoing area of research. For instance, if a giant impact caused the rapid spin, did it happen before or after differentiation? An impact on an undifferentiated object might have different outcomes than one on a differentiated body. The potentially non-spherical shape also relates to internal structure. If the shape is due to rotational flattening, the degree of flattening is influenced by how the mass is distributed internally. A differentiated object with a dense core might exhibit different flattening than a homogeneous one spinning at the same rate. Determining Varuna's internal structure is incredibly challenging as it requires indirect methods. Scientists use models that combine observational constraints like size, mass derived from density estimates, rotation rate, and shape to infer possible internal configurations. The potentially low bulk density, if confirmed, tends to favor a less differentiated or more porous structure, but the rapid spin seems to imply a history of significant energy input, which could also lead to differentiation. It's a complex interplay of factors, and without more direct measurements like those a visiting spacecraft could provide, the interior of Varuna remains hidden. The mystery of Varuna's internal structure is fundamental to understanding its entire evolution. Was it a passive accumulator of material remaining largely unchanged inside? Or did it undergo a period of internal heating and differentiation, transforming its initial composition into a layered structure? The answer speaks to the thermal history of this distant dwarf planet and places it somewhere along the spectrum of icy world evolution, from primitive building block to internally processed body. This unseen interior holds secrets that profoundly impact every other mystery we observe on its surface and in its motion. Delving deeper into the confusing signals from Varuna, we arrive at mystery number 20, the riddle of its infrared spectrum. While visible light gives us clues about color and reflectivity, infrared light tells us about temperature and, crucially, can reveal the presence of specific chemical bonds and compounds. When astronomers point infrared telescopes at Varuna and analyze the light that's either emitted or reflected, they get a spectral fingerprint of its surface materials, revealing which wavelengths of infrared light are absorbed or reflected most strongly. For an icy body in the outer solar system, we anticipate certain characteristic absorption features in the infrared spectrum, corresponding to the vibrations and rotations of molecules found in common ices like water, methane, nitrogen, and carbon monoxide. These molecules absorb infrared light at specific, well-known wavelengths, leaving telltale dips or valleys in the spectrum. It's like scanning a barcode to identify a product. Each molecule has its unique infrared barcode. However, Varuna's infrared spectrum has been stubbornly uncooperative. The signals are very faint, as expected from such a cold and distant object, making the data noisy and challenging to interpret. But even with the best data available, the expected clear absorption features for common ices are either weak, shifted, or simply absent. We don't see the crisp, deep valleys in the spectrum that we'd expect if Varuna were covered in relatively pure common ices. This spectral anomaly is one of the most frustrating puzzles for scientists trying to understand Varuna's composition. It leaves us wondering, are the conventional ices truly missing from its surface, or are they present but hidden or altered in some way? One explanation, as we've touched upon, is that the surface is dominated by something else entirely, those dark, reddish tholins. These complex organic polymers don't have the same sharp, distinct infrared absorption features as simple ices. Their spectra tend to be broader and less defined, potentially masking or altering the signatures of any underlying ice. If the tholin layer is thick and covers most of the surface, the infrared light might not be penetrating deep enough to interact significantly with the ice below, or the light reflected back after interacting with the tholins swamps out any faint signal from the ice. Imagine trying to read a label through a piece of smoky glass. The glass distorts and obscures what's behind it. The tholin layer might be acting like that smoky glass for Varuna's infrared spectrum. Another possibility is that the ice on Varuna isn't in a standard form. At the extremely low temperatures of the Kuiper Belt, water ice can exist in different crystalline structures than the hexagonal ice we're familiar with on Earth, like snowflakes. It can also exist as amorphous ice, a non-crystalline, glassy form. The infrared spectral signatures of these different ice structures can vary. If Varuna's ice is primarily in an unusual crystalline phase or is largely amorphous, its spectral features might be shifted or broadened compared to the standard spectra we use for comparison, making them harder to identify definitively. The thermal history of Varuna, how quickly it cooled after formation, whether it experienced significant internal heating, or if it underwent any cryovolcanic activity would influence the structure of its ice. Furthermore, the ice might not be pure. If it's intimately mixed with rocky dust, organic compounds, or other non-ice materials, the spectral signature of the ice itself can be affected, becoming weaker or distorted. This dirty ice scenario is plausible, aligning with the idea of a surface contaminated with tholins or rocky debris. The faint infrared signals could also simply be an artifact of measurement limitations. Obtaining high-quality infrared spectra from an object as distant and cold as Varuna is at the very edge of our current technological capabilities. The data is inherently noisy, and subtle spectral features can be easily lost in that noise. It's possible that with more sensitive instruments in the future, clearer ice signatures might emerge. However, the persistent difficulty in finding clear evidence for common ices, especially water ice, in Varuna's infrared spectrum remains a key mystery. It forces astronomers to consider more exotic possibilities for its surface composition. Could there be significant amounts of other, less common frozen volatiles that we don't fully understand? Could the surface be dominated by non-ice materials to an extent we haven't considered? The infrared spectrum is a critical piece of the puzzle, but right now, it's painting a picture that doesn't quite match our expectations, suggesting that Varuna's surface chemistry is more complex and perhaps more unusual than we initially assumed for a large Kuiper Belt object. This spectral puzzle challenges our fundamental assumptions about the composition of bodies forming in the far reaches of the solar system, hinting that Varuna might be built from a different mix of ingredients or has undergone unique processing, making it a truly extraordinary world. Adding to the list of Varuna's baffling behaviors is mystery number 21, the puzzling vanishing act of its light curve over time. Remember how we talked about Varuna's light curve, the way its brightness changes as it rotates, providing clues about its shape and surface features. Initially, when astronomers first started observing Varuna in detail after its discovery, they saw a light curve that showed significant variations in brightness, variations that were crucial for determining its rapid rotation period and hinted at a non-spherical shape or prominent dark and bright spots. These early light curves were quite pronounced, giving scientists a solid handle on its rotational period of just over 3 hours. However, remarkably, when astronomers went back to observe Varuna years later, expecting to see the same consistent pattern of brightness variations, the light curve seemed to have diminished. The variations weren't as strong, the peaks and valleys weren't as deep. It was as if the features on the surface that were causing the brightness changes had somehow become less prominent, or Varuna itself had changed its appearance. This isn't something you typically expect from a solid, unchanging object far out in the cold vacuum of space. A stable, rocky or icy body should show a consistent light curve over decades, assuming its shape and fixed surface features are the primary cause of the variations. The observation that Varuna's light curve has changed significantly is a major anomaly that demands an explanation, pointing towards dynamic processes happening on its surface or perhaps even subtle shifts in our viewing geometry in relation to its rotation axis. One leading theory links the changing light curve to potential seasonal variations on Varuna. While Varuna is incredibly far from the Sun, its orbit isn't perfectly circular, and it also has that potential axial tilt we discussed earlier. This combination means that different parts of Varuna's surface receive slightly different amounts of sunlight over the course of its long year. If Varuna has volatile ices on its surface, like methane or nitrogen, and if its axial tilt is significant, these ices could be undergoing seasonal cycles of sublimation and condensation. Imagine a polar region that is tilted towards the Sun for part of Varuna's orbit. The increased sunlight, however meager, could cause volatile ices in that region to sublimate, perhaps exposing darker material underneath or altering the reflectivity of the surface. Later, as that region tilts away from the Sun, those same volatiles might condense back onto the surface, forming a layer of fresh, brighter ice. These ongoing, subtle processes of deposition and sublimation could change the distribution of bright and dark patches on Varuna's surface over time, directly impacting the amplitude of the observed light curve. If the features causing the strongest variations in the earlier observations were related to temporary patches of volatile ice, and those patches have since sublimated or shifted due to seasonal warming and cooling, it would explain why the light curve variations are less pronounced in later observations. Another possibility is that the surface itself is undergoing some form of slower, secular change, perhaps related to space weathering or the accumulation of tholins, but happening at a discernible rate over years or decades. While we expect processes like radiation processing to occur over billions of years, perhaps there are aspects of Varuna's specific environment or composition that cause more rapid surface alteration in certain areas. For example, if cryovolcanic activity is intermittently exposing fresh ice, the subsequent darkening of that ice by radiation could alter the contrast on the surface over relatively short timescales. However, explaining a significant decrease in light curve amplitude through general darkening is less straightforward than explaining it through the disappearance or redistribution of bright features. It's also worth considering whether the apparent change in the light curve is somehow related to our viewing angle in relation to Varuna's potentially tilted rotation axis as it moves along its orbit. As Varuna orbits the Sun, and as we orbit the Sun on Earth, our perspective on Varuna changes. If Varuna is non-spherical, our view of its shape and surface features will vary depending on our angle. However, changes in viewing geometry are predictable, and astronomers account for them. The difficulty is that if the rotation axis is highly tilted and the shape is irregular, the combined effect on the observed light curve can be complex. While changes in viewing geometry might alter the appearance of the light curve, they wouldn't typically cause the underlying surface contrast variations to vanish unless our view was becoming perfectly aligned with a less varied part of the surface. Ultimately, the vanishing act of Varuna's light curve is a compelling piece of evidence that this distant world is not simply a static chunk of ice. It suggests that its surface is dynamic, undergoing changes that are significant enough to be detected from billions of miles away over observation periods spanning mere years. Whether driven by subtle seasonal cycles of volatile ice or other less understood processes, this shifting light curve adds another layer to Varuna's complex portrait, hinting at a world where surface properties are not set in stone, but are instead slowly evolving under the feeble distant sunlight. It demands further monitoring to see if the variations return or continue to diminish, providing critical data input for models of surface evolution on the coldest, most distant worlds in our solar system. Following the perplexing mystery of its changing light curve, which hints at a dynamic surface, we encounter mystery number 22, the curious case of Varuna's missing family. As we discussed earlier when pondering Varuna's origin, some Kuiper Belt objects have been involved in massive collisions that shattered a larger parent body, creating a family of smaller fragments that continue to orbit the Sun along similar paths. The most prominent example is the Haumea family. Haumea is a large dwarf planet with a very rapid spin, a non-spherical shape, and a couple of moons thought to have been spun off or formed from impact debris. Significantly, Haumea is also accompanied by a collection of smaller KBOs that share its orbital characteristics and surface properties, strongly suggesting they are pieces of a larger body that broke apart in a collision billions of years ago. Think of it like the remnants of a shattered vase. The pieces might scatter, but they originated from the same object and share similar material. Given that many of Varuna's characteristics, its rapid spin, potential non-spherical shape, and perhaps even its density point towards a history involving a major impact, you might logically expect to find similar collision fragments orbiting in Varuna's vicinity. If a giant impact was powerful enough to set Varuna spinning wildly and possibly deform its shape, it seems highly probable that such an event would also have created a significant amount of debris, forming a family of smaller objects orbiting on similar trajectories. Yet, despite dedicated searches, astronomers have not identified a clear, associated family of smaller KBOs orbiting near Varuna. It stands alone as a major object without a retinue of smaller fragments tracing its orbital path. This absence is puzzling, especially when contrasted with objects like Haumea, where the evidence for a major collision and subsequent fragmentation is so clear. So, if Varuna was indeed involved in a massive impact event, where did all the expected debris go? One plausible explanation is that the collision that shaped Varuna was so energetic that it didn't just fragment the parent body. It scattered the resulting debris much more widely than in the case of the Haumea family. Perhaps the impact velocity was higher, or the angle of impact was different, resulting in fragments being ejected at higher speeds and on trajectories that diverged significantly from Varuna's final orbit. Instead of staying clustered together, the collision products could have been flung across a broader region of the Kuiper Belt, or even ejected entirely from the solar system. In this scenario, the family is still out there, but its members are too dispersed, too far from Varuna, or too faint to be easily linked back to the original event through their current orbital similarities to Varuna alone. It would be like the pieces of that shattered vase being not just scattered across a room, but across an entire football field. it's much harder to identify them as belonging to the same object. Another possibility is that the assumed impact scenario for Varuna was different from the one that created the Haumea family. Perhaps the collision involved a different type of object or occurred at a different stage in the Kuiper Belt's evolution. The amount and size distribution of debris produced in a collision depend heavily on the size and composition of the colliding bodies and the energy of the impact. It's conceivable that the specific parameters of the impact that affected Varuna resulted in very little large, identifiable debris, perhaps producing mostly fine dust that has long since dispersed or is undetectable. There's also the possibility, however remote, that the event that caused Varuna's rapid spin wasn't a single large impact but a cumulative effect of multiple smaller impacts or even tidal forces from a close encounter with a larger object that didn't result in catastrophic fragmentation. While a single large impact remains the most favored explanation for such a rapid spin in one go, we shouldn't entirely rule out alternative scenarios that might not produce a large family of fragments. The lack of a detectable family around Varuna is a significant constraint on the impact hypothesis. If a major collision is the explanation for many of Varuna's anomalies, then the absence of its expected collisional brethren demands a more energetic version of that impact scenario, one that resulted in widespread scattering of debris. It forces scientists to refine their models of collisions in the Kuiper Belt, considering events powerful enough to reshape a dwarf planet and scatter its remnants far and wide. This missing family isn't just an oversight, it's a clue that the story of Varuna's turbulent past, if indeed it was shaped by a collision, involves processes that were perhaps even more violent and dispersive than those that affected other KBOs, adding another layer of complexity to the narrative of this truly enigmatic world. Following the puzzle of Varuna's missing family of collisional fragments, which implies debris was scattered far and wide, we arrive at an equally intriguing mystery number 23, the ghostly halo or potential faint debris ring that some astronomers believe might exist around Varuna. While no orbiting moons have been definitively detected, there have been tantalizing, albeit unconfirmed, reports and hints in observational data suggesting the presence of a tenuous ring of dust or small particles encircling this distant dwarf planet. If true, this would be a remarkable finding. Rings are typically associated with giant planets like Saturn, Jupiter, Uranus, and Neptune, or sometimes with much smaller bodies like centaurs or even asteroids where tidal forces or impacts can create temporary rings. Finding a persistent ring system around a dwarf planet in the Kuiper Belt like Varuna would be a significant and unexpected discovery, adding yet another layer to its already complex nature. The evidence for this potential ghostly halo is, at present, extremely weak and based on very challenging observations. It comes primarily from subtle variations in Varuna's light curve that are not fully explained by its rotation and shape alone, or perhaps from extremely faint signals detected in the scattered light around Varuna during specific high-sensitivity observations. These hints are on the ragged edge of detectability with current telescopes, and confirming or refuting their existence requires pushing the limits of astronomical instruments and data analysis techniques. Imagine trying to spot a faint puff of smoke around a distant campfire on a hazy night. It requires perfect conditions and sharp eyes. The challenges are immense. Varuna's vast distance means its faint light is spread out and easily lost in the background noise of space, and any potential ring would be even fainter, composed of tiny particles that reflect very little sunlight. The same difficulties that plague the search for faint moons make the search for an even fainter, more diffuse ring incredibly difficult. If a faint ring system does exist around Varuna, its presence would immediately raise questions about its origin. Unlike the massive, long-lived rings of giant planets which are shaped by the gravity of the planet and its moons, a ring around a dwarf planet would likely require a more recent or ongoing source of material. One possible origin links back to the rapid spin. If Varuna is spinning so fast that the centrifugal force at its equator is significant, perhaps even close to overcoming gravity in some areas, tiny particles or even larger chunks of material could be shed from the surface, forming a diffuse ring. This is similar to how some asteroids spinning very rapidly have been observed to shed material, creating temporary debris clouds. For Varuna, its persistent rapid spin could be a continuous source of material for a faint, diffuse ring. The size and composition of the particles in such a rotationally shed ring would depend on the materials available on Varuna's surface and the forces acting upon them. Another potential origin for a ring system, even a faint one, involves impacts. If Varuna is periodically bombarded by small meteoroids or even larger objects, these impacts could kick up dust and debris from the surface or create small fragments that go into orbit around Varuna. A series of such impacts over time could maintain a tenuous ring of material. This ring might be temporary, slowly dissipating over time as particles are lost to space or fall back onto the surface, but continuous bombardment could replenish it. This scenario aligns with the idea of Varuna having experienced impacts in the past, though it would suggest ongoing, perhaps more frequent, smaller impacts are also at play. A third possibility is related to the potential presence of a moon or a close binary companion that is either too small to detect directly or is currently undiscovered. Tidal forces exerted by a moon or companion could potentially disrupt material on Varuna's surface or even disrupt the moon itself if it's orbiting too close, creating a debris ring. This is how the rings of some smaller bodies are thought to have formed. However, given the lack of a detected moon, this explanation relies on the existence of another unseen object. The mystery of the ghostly halo around Varuna is a test of our observational limits and our understanding of how ring systems can form and persist around smaller celestial bodies. If future, more sensitive observations confirm the existence of even a faint ring, it would provide compelling evidence for ongoing activity or processes around Varuna, whether its material being shed by its rapid spin, generated by impacts, or somehow related to unseen companions. It would add another layer to the narrative of Varuna as a uniquely dynamic world in the frigid outer solar system, far from the sun's powerful influence, yet potentially surrounded by its own subtle, enigmatic ring of debris. Following the potential secret of a ghostly debris ring, we dive into mystery number 24, the puzzling riddle of Varuna's thermal inertia. Now, thermal inertia sounds complicated, but it's essentially a measure of how quickly a material heats up or cools down when it's exposed to changes in temperature. Think about sand on a beach versus a swimming pool. The sand heats up very quickly under the sun and cools down quickly after sunset. It has low thermal inertia. The water in the pool heats up and cools down much more slowly. It has high thermal inertia. For a distant object like Varuna, its thermal inertia tells us something about the properties of its surface material, how easily heat penetrates its outermost layers, and how quickly its surface temperature responds to the changing amount of sunlight it receives as it rotates and orbits. Based on our understanding of icy, rocky bodies in the outer solar system, scientists can predict a likely range for Varuna's thermal inertia. However, when they analyze the subtle ways Varuna's temperature appears to respond to sunlight, for example, how much it cools off on its night side compared to its sunlit side, or how its overall temperature changes as it moves closer to and farther from the sun in its orbit, the observations don't quite match the predictions. Varuna's surface seems to be behaving in a way that suggests its thermal inertia is either unexpectedly high or low, meaning it's either slower or faster to change temperature than expected. This discrepancy is another puzzle piece that points to unusual surface properties or perhaps unforeseen processes influencing its thermal state. One major factor influencing thermal inertia is the nature of the surface layer, specifically what astronomers call the regolith. On most solid bodies in the solar system, the surface isn't solid rock or ice. It's covered by a layer of loose, fragmented material created by billions of years of impact. This layer, the regolith, acts as an insulator. A fine, dusty regolith with lots of empty space between the particles is a very good insulator, slowing down the transfer of heat into and out of the surface. Think of how a layer of snow on the ground insulates the earth beneath it. If Varuna has a very fine, powdery regolith layer, it would have low thermal inertia. The very surface would heat and cool quickly, but heat wouldn't penetrate easily into the subsurface. Conversely, if the surface material is more compacted, made of larger chunks, or if it's more like solid ice or rock with less porosity, it would transfer heat more efficiently, resulting in higher thermal inertia. The observed thermal behavior of Varuna, if it indicates lower thermal inertia than expected, could suggest that its surface is covered in a very fine, insulating regolith. This might seem counterintuitive given the potential for large impacts in its past, which you might expect to create larger fragments. However, billions of years of micrometeoroid bombardment can grind down larger debris into fine dust. Also, if Varuna has experienced cryovolcanism, any erupted material could freeze into a fine-grained texture upon hitting the vacuum. If its thermal inertia is higher than expected, it could suggest a more consolidated surface layer, perhaps less porous regolith, or even patches of exposed, relatively solid ice or rock. Another factor that could complicate the thermal inertia calculation is the potential for internal heat flow reaching the surface. While Varuna is distant and cold, if it has some residual internal heat from formation or radioactive decay, and if that heat is somehow making its way to the surface, it could subtly influence the surface temperature and make it seem warmer, or its response to solar heating different than models based purely on external warming predict. However, the radio silence we discussed earlier might argue against significant ongoing internal heat flow. The mystery of Varuna's thermal inertia is intimately connected to the nature of its regolith and potential subsurface processes. It asks what kind of blanket covers this distant world and how effectively that blanket insulates it from the vacuum of space and the faint warmth of the distant sun. Understanding its thermal inertia is crucial for building accurate models of how heat flows within Varuna and how its surface composition and structure vary with depth. It's a subtle measurement, hidden in the very way Varuna warms and cools, but it holds important clues about the physical state of its outermost layers, adding another piece to the complex puzzle of this enigmatic dwarf planet. Building on the clues from Varuna's rapid spin, its potentially non-spherical shape, and the puzzling characteristics of its surface and presumed interior, we arrive at mystery number 25. The profound challenge Varuna's very existence, with all its peculiar traits, poses to our current models of how dwarf planets and other large Kuiper Belt objects form. Based on simulations and our understanding of the early solar nebula, we have developed sophisticated models for the accretion process, the gradual sticking together of dust and ice particles to form increasingly larger bodies. These models predict that objects of Varuna's size in the frigid environment of the Kuiper Belt should generally have certain characteristics: a more moderate rotation rate, a shape closer to spherical unless very significantly impacted, and possibly a retinue of moons formed either from an impact or capture. They also predict a certain range of densities and surface compositions based on the available materials and the thermal history of the object. Varuna seems to defy these expectations on multiple fronts simultaneously. Its hyperspeed rotation, its apparently dark and patchy surface, its potential lack of moons, and the oddities of its estimated density and temperature combine to create a picture that doesn't fit neatly into the standard narratives of outer solar system formation. It's like finding a brightly colored, rapidly vibrating, oddly shaped rock in a collection of smooth, dull, slow-spinning stones. It forces scientists to ask, is there something fundamentally wrong with our models, or did Varuna experience a unique history that set it apart from its peers? One way to reconcile Varuna's existence with our models is to accept that its formation and evolution were dominated by extremely energetic, relatively low probability events. The giant impact hypothesis, which we've touched on multiple times, is a prime example. If a massive collision occurred relatively late in Varuna's formation or even after it had largely accreted, this single event could explain the rapid spin, the non-spherical shape, the potential absence of moons due to ejection or destruction, and perhaps even aspects of its surface composition if the impact exposed or processed underlying materials differently. In this view, Varuna isn't a typical outcome of Kuiper Belt formation, but rather an object whose initial, more standard characteristics were dramatically altered by a rare, catastrophic event. It's a survivor of a cosmic smash-up, its current state a testament to the violence of the early solar system. This would mean our formation models might be correct for most KBOs, but Varuna represents an outlier shaped by subsequent events. Another perspective suggests that Varuna's formation environment or process was itself unusual. Perhaps it accreted material differently than other KBOs, in a way that naturally led to a higher initial spin rate or a less consolidated internal structure, contributing to its potential low density. Could it have formed in a region of the solar nebula where the distribution of materials or the accretion velocities were different? Or perhaps it formed closer to the Sun and was subsequently scattered outwards into the Kuiper Belt. This is where migration theories come into play. As the giant planets migrated outwards billions of years ago, they would have scattered countless smaller objects. If Varuna formed closer in, it might have incorporated a different mix of materials or experienced a warmer thermal history that influenced its initial composition and structure before being flung into the outer reaches. An object scattered from closer in might have properties that differ from those that formed in situ within the Kuiper Belt. Its orbit, being more eccentric and inclined than classical KBOs, slightly aligns with the expectation for a scattered object, adding some weight to this idea. However, explaining all of Varuna's peculiarities solely through a different formation location or process without involving a major impact is challenging, particularly the extreme rapid spin. The mystery of why Varuna exists in its current state, with its collection of anomalies, is a powerful driver for refining our models of solar system formation and evolution. It forces us to consider the full range of processes that can occur, from relatively gentle accretion to violent collisions and large-scale planetary migration. Is Varuna a product of standard formation followed by a rare impact? Is it an object formed differently due to location or process, or is it a combination of these factors? Each possibility requires different assumptions about the conditions and events in the early solar system. Varuna acts as a crucial test case, a real-world example that pushes the boundaries of our theoretical understanding and highlights the diversity and complexity of the objects residing in the distant, frigid realm of the Kuiper Belt. Its very presence, with all its unexplained mysteries, is a challenge to our current knowledge, urging us to look closer and think differently about how worlds are built in the dark, outer reaches of our cosmic home. Stepping back to Varuna's surface properties, we zero in on mystery number 26, the cryptic way Varuna reflects light at certain wavelengths. When astronomers analyze the spectrum of light bouncing off Varuna, it's not just the overall redness or darkness that's puzzling. It's the subtle yet significant deviations in how it reflects light at specific colors or wavelengths. While the infrared spectrum shows a lack of expected ice signatures, even in visible and near-infrared light, there are peculiar patterns. The way Varuna reflects or absorbs light doesn't perfectly match the spectral fingerprints of known materials that we'd expect to find on an icy, rocky body in the outer solar system. It's as if Varuna is reflecting with a slightly off-key note, a spectral anomaly that hints at something unusual about its surface composition or structure that isn't immediately obvious. One possible explanation for these cryptic reflections lies in the physical properties of the surface materials, specifically the grain size of the particles making up its regolith or outermost layer. The way light scattering works, particularly for icy or rocky materials, is highly dependent on the size of the individual grains or particles. Imagine light hitting a pile of fine powder versus a pile of larger pebbles made of the same material. The light will interact with the surfaces differently, and the overall amount of light reflected and how it's reflected at different wavelengths will vary. If Varuna's surface is covered in ice or rocky particles with an unusually fine grain size, perhaps like talcum powder, it could cause light to be scattered in a way that produces these observed spectral oddities. A very fine-grained surface tends to scatter light more evenly across different angles, which can subtly alter how its total spectrum appears to a distant observer. Conversely, a coarser-grained surface might exhibit different scattering properties. The size of the grains is influenced by processes like the rate of micrometeoroid bombardment, which grinds down surface materials, or potential cryovolcanic activity, which might deposit fine-grained material on the surface. So, the cryptic reflections could be an indirect clue to the texture of Varuna's surface regolith. Another compelling explanation delves beneath the very outermost layer, considering the role of subsurface scattering. If the dark, primary surface layer of Varuna is somewhat transparent or porous, some sunlight might be penetrating this layer and interacting with materials just below the surface. These materials could have a different composition or physical state than the surface layer. Perhaps they are more reflective ice, or ice with a different impurity mix. As the light scatters off these subsurface materials and then makes its way back out through the darker surface layer, its spectral signature could be altered in a way that creates the observed anomalies. Think of light filtering through a slightly murky pond. The light that reaches the bottom and bounces back is changed by the water and any particles suspended in it. Similarly, light interacting with a subsurface layer on Varuna would pick up the spectral characteristics of those materials and then be modified as it passes back through the outer layer. This scenario would explain why we don't see clear, strong signatures of expected surface materials, but instead see a kind of blended, cryptic spectrum. It suggests that our telescopes are seeing a combination of light reflected directly off the dark surface and light that has taken a more complex path, penetrating slightly below the surface before returning to space. The specific wavelengths where Varuna shows these cryptic reflections are particularly important. By carefully analyzing which parts of the spectrum are behaving unexpectedly, scientists can try to narrow down the possibilities for what materials might be present in unusual grain sizes or just below the surface. Different types of ice, different organic compounds, or different mineral mixtures all have unique spectral properties. Comparing Varuna's cryptic spectrum to laboratory measurements of various materials under simulated conditions is a key part of trying to solve this mystery. This puzzle of the cryptic light reflections is closely linked to many other Varuna enigmas. Its dark surface, the potential for bright spots, the lack of clear ice signatures in the infrared, and its speculated surface texture and regolith properties. It reinforces the idea that Varuna's surface is not a simple, uniform layer of ice and rock, but a complex, potentially layered environment shaped by a variety of processes. The subtle ways it reflects light at specific wavelengths are like faint whispers from this distant world, hinting at the composition and structure just waiting to be fully understood, pushing the limits of our ability to read the story written in starlight reflected across billions of miles. Continuing our descent into the mysteries of Varuna's surface, we encounter mystery number 27. The potential presence of exotic surface materials not commonly found or expected on Kuiper Belt objects. While we largely anticipate finding various forms of water ice, methane ice, nitrogen ice, and potentially some rocky silicates and radiation-processed organics like tholins on KBOs. The cryptic spectral signatures and other unusual properties of Varuna raise the intriguing possibility that its surface might host materials that are less common or even entirely unexpected in this remote region. The solar system. What else could be lurking on Varuna's surface, contributing to its enigmatic nature? One speculation centers on hydrocarbons heavier and more complex than methane or ethane. While tholins are complex organic polymers formed from simpler hydrocarbons, Varuna's surface might contain other types of higher molecular weight hydrocarbons or even frozen organic molecules formed through different processes. These could have distinct spectral features in the infrared and visible light that don't match our standard references, contributing to the cryptic reflections. The conditions in the early solar nebula where Varuna formed, or the specific types of radiation processing it has undergone, might have favored the formation or accumulation of these more complex organics. Identifying such materials would provide valuable insights into the chemistry of the outer solar system and the building blocks available for planetesimal formation beyond the traditional frost line where water ice condenses. Another possibility, though more speculative, involves less common frozen volatiles. While methane and nitrogen are relatively abundant, could Varuna harbor significant amounts of other frozen gases like ammonia, hydrogen sulfide, or even noble gases like argon or neon trapped within its ice? The presence and abundance of these volatiles would depend heavily on the temperature and pressure conditions in the specific region of the solar nebula where Varuna originated. If Varuna formed from material that condensed at slightly different temperatures or pressures than other KBOs, it might have incorporated a unique mix of these less common volatiles into its structure. Frozen ammonia, for instance, can affect the physical properties of water ice, lowering its melting point and potentially playing a role in cryovolcanic activity. Detecting the spectral signatures of these less common volatiles is even more challenging than for water or methane, as their features might be weaker or overlap with other materials. There's also the question of non-ice components. While KBOs are predominantly icy, they also contain rocky material. The composition of this rocky component on Varuna might be unusual. Could it contain specific types of minerals or silicates that have unique spectral properties, interacting with light in unexpected ways? Perhaps altered minerals, formed through past interactions with liquid water, even fleetingly during formation or impact events, or through long-term radiation exposure, are present on the surface and contributing to the spectral anomalies. The potential presence of these exotic materials isn't just a chemical curiosity. It fundamentally impacts our understanding of where and how Varuna formed. If it contains materials not typically seen on other KBOs, it could mean it originated in a different part of the early solar nebula, perhaps closer to the Sun before being scattered outward, or in a region with a localized, unusual composition. It could also mean that the processes of formation and evolution on Varuna, including radiation processing or internal activity, have uniquely altered its surface chemistry. Current efforts to identify these potential exotic materials involve painstaking analysis of faint spectral data, searching for subtle features that don't fit the standard models. It also involves laboratory experiments, zapping mixtures of expected and potential Varunian materials with radiation under cold vacuum conditions to see what kind of spectral signatures they produce. The mystery of Varuna's potential exotic surface materials is a frontier of exploration, pushing us to consider the full chemical diversity that might be hidden on the surfaces of distant, cold worlds and challenging our assumptions about the universal nature of materials in the outer solar system. Discovering such materials would be a scientific bombshell, opening up entirely new avenues of research into the formation and evolution of planetary bodies far from the Sun's warmth, making Varuna even more of a Rosetta Stone for understanding the Kuiper Belt. Stepping back to a broader perspective, we arrive at mystery number 28, the puzzle of Varuna's place within the larger context of the Kuiper Belt structure and evolution. The Kuiper Belt isn't just a random collection of icy bodies. It has a complex structure with different populations of objects residing in distinct orbital regions. There are the classical KBOs in relatively stable, low eccentricity, low inclination orbits, resonant KBOs like Pluto, whose orbits are locked in gravitational resonance with Neptune, and scattered disk objects which are on highly elliptical and inclined orbits, believed to have been scattered outwards by Neptune's migration. Where does Varuna fit into this picture, and what can its story tell us about the forces that shaped the entire region? Varuna's orbit is somewhat enigmatic in this context. While it's broadly considered a classical KBO because its orbit isn't in a strong, stable resonance with Neptune, its orbital parameters, particularly its noticeable eccentricity and inclination, are higher than those of the cold classical population, which are thought to be the most pristine remnants of the early solar system, largely undisturbed since their formation. Varuna's orbit sits somewhat awkwardly between the calm of the cold classicals and the turmoil of the scattered disk objects. This intermediate orbital state raises fundamental questions about its history. Was Varuna originally a cold classical object that was subtly perturbed later in its history, perhaps by a weak, temporary resonance encounter with a giant planet or a close pass by another large KBO? If so, the forces required to nudge it into its current orbit, while not scattering it completely into the scattered disk, would still be significant and tell us about the dynamic environment of the Kuiper Belt even after the main period of planetary migration. Alternatively, could Varuna be an object that was scattered outwards from closer in, but then evolved into a more stable, albeit not perfectly circular or flat, orbit within the classical belt? This scenario would fit with the idea that its formation location was different from the majority of classical KBOs. The process of scattering and subsequent Chinese letter into a stable orbit is complex and depends on the precise timing and nature of gravitational interactions. Varuna's current orbit could represent one possible outcome of this turbulent scattering process. Its orbital characteristics, in combination with its physical properties like rapid spin and potential fragmentation origin, could serve as a test case for models simulating the outward migration of giant planets and their impact on the primordial population of the Kuiper Belt. Scientists try to run these simulations, starting with different initial configurations of planets and planetesimals, to see if they can reproduce the observed distribution of objects, including those with orbits like Varuna's. The existence of an object with Varuna's unique combination of orbital and physical properties challenges our understanding of how objects are sorted and retained in the different subdivisions of the Kuiper Belt. Is there a specific region within the early solar nebula from which objects with Varuna-like characteristics originate? Are there specific types of violent events or gravitational interactions that are more likely to produce and place objects like Varuna into their current orbits? Or does Varuna simply represent the extreme end of the natural variation within the classical KBO population, an object that happened to experience a rare alignment of factors that led to its current state? Answering these questions requires a deeper understanding of the entire population of KBOs, not just individual objects. By studying the distribution and properties of hundreds or thousands of KBOs, astronomers can look for patterns and correlations that might reveal the underlying processes. Varuna, with its distinct properties, acts as a crucial data point, an object that our models must be able to account for. It's not enough for a model to explain the cold classicals or the scattered disk. It must also be able to explain how an object like Varuna, with its apparently contradictory calm orbit and turbulent history, ended up where it is. Its location and characteristics within the Kuiper Belt are a profound mystery, a silent witness to the large-scale gravitational dance that shaped the outer reaches of our solar system billions of years ago, and a key to unlocking the secrets of that ancient cosmic ballet. From its place within the grand architecture of the Kuiper Belt, we turn to a more introspective mystery number 29, the scientific debate surrounding the very classification of Varuna. Is it a dwarf planet? Or is it something else entirely? The official definition of a dwarf planet, established by the International Astronomical Union in 2006, states that a celestial body must meet 4 criteria to be classified as such. It must orbit the Sun, it must not be a moon, it must have sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium nearly round shape, must not have cleared the neighborhood around its orbit. Varuna clearly meets the first 2 criteria. It orbits the Sun and is not a moon. The debate arises with the 3rd and 4th criteria, and this is where all of Varuna's mysteries come into play. The 3rd criterion requires the object to be massive enough to be rounded by its own gravity into a state of hydrostatic equilibrium. Our estimates of Varuna's size and mass are uncertain, as we've discussed. Thermal measurements suggest a diameter in the range of 800 to 900 kilometers, and density estimates, while also uncertain, suggest a significant mass. For an icy/rocky body, reaching hydrostatic equilibrium typically occurs at a diameter somewhere between 400 and 1,000 kilometers, depending on the composition and internal structure. Given the current estimates for Varuna's size, it's generally considered massive enough to have achieved this rounded shape, or at least to be in the process of achieving it over cosmic timescales. However, the hints of a non-spherical shape, potentially due to its rapid spin or a past impact, complicate this. If Varuna is significantly non-spherical due to these factors, does it technically meet the hydrostatic equilibrium criterion? Some interpretations of the definition allow for deviations from a perfect sphere due to rotation or impacts, as long as the underlying mass is sufficient for gravity to tend towards roundness. Others argue for a stricter interpretation. The uncertainty in Varuna's precise shape and internal structure fuels this part of the debate. The 4th criterion, that a dwarf planet must not have cleared the neighborhood around its orbit, is the main point of distinction separating dwarf planets like Pluto and Eris from the 8 planets. A full-fledged planet is gravitationally dominant in its orbital zone, having either accreted or ejected most of the other smaller objects. Dwarf planets coexist with many other objects in their orbital paths. Varuna, residing in the Kuiper Belt, is clearly in an environment with countless other objects in similar orbits. Therefore, it easily meets this 4th criterion for being a dwarf planet. It has not cleared its orbital neighborhood. So, the classification debate for Varuna primarily hinges on whether its estimated size and potential shape definitively confirm that it has achieved hydrostatic equilibrium. While the current leading estimates suggest it probably has, the uncertainties leave room for scientific discussion. Adding to the complexity is the possibility that Varuna's rapid spin might actually prevent it from achieving a perfectly hydrostatic shape, even if it has sufficient mass. The definition of hydrostatic equilibrium itself, particularly as it applies to cold, solid, rotating bodies in space, is an area of ongoing scientific refinement. Different models for determining whether an object is in hydrostatic equilibrium yield slightly different results depending on the assumed composition and rotation rate. Currently, Varuna is listed as a dwarf planet candidate by many astronomers and is included in lists of trans-Neptunian objects likely to be dwarf planets based on its estimated size. However, until its mass and shape can be determined with higher precision, and until we have a more universally agreed upon method for assessing hydrostatic equilibrium in such objects, there will remain a degree of scientific debate about its definitive classification. This mystery highlights the challenges of categorizing celestial bodies in newly explored regions like the Kuiper Belt, where objects exhibit a wide range of properties and behaviors. Varuna's classification isn't just a matter of terminology. It reflects our evolving understanding of what constitutes a dwarf planet and how these definitions apply to the diverse and often surprising objects we are discovering in the outer solar system. It's a reminder that even the most fundamental questions about these distant worlds are still subjects of active scientific investigation and debate. Finally, we arrive at mystery number 30, the grand culmination of all Varuna's puzzles, the ultimate question of what this distant dwarf planet can reveal about the formation and evolution of planetary systems in general, not just our own solar system, but potentially those around other stars. Varuna is more than just an oddity in our cosmic backyard. It's a natural laboratory operating under extreme conditions, immense cold, low light levels, and a vast timescale of billions of years. By studying its peculiar properties, we gain insights that can be applied to our understanding of how icy bodies form and evolve in the outer regions of any stellar system. The Kuiper Belt itself is thought to be analogous in some ways to the debris disks observed around many other stars, vast reservoirs of cold material that are the remnants of planet formation. These debris disks are often too distant for us to see individual objects, but we infer their existence and properties from the light they scatter and emit. Varuna provides a tangible example of the kind of object that might inhabit these distant disks. Its rapid spin, dark surface, potential internal structure, and orbital oddities are not just unique to our solar system. They represent potential outcomes of formation and evolutionary processes that could occur anywhere planet formation takes place. For example, if Varuna's rapid spin was indeed caused by a giant impact, it tells us that such energetic collisions were a significant factor in the early history of the outer solar system. Are such impacts common in the outer regions of other stellar systems? Studying the frequency of rapidly rotating, potentially fragmented bodies like Varuna in our own Kuiper Belt can help us estimate the likelihood of similar events occurring elsewhere. This has implications for understanding the stirring and evolution of debris disks and the processes that might lead to the formation of planets or larger bodies in those systems. Similarly, Varuna's dark, tholin-rich surface and its lack of expected ice signatures provide clues about the effects of long-term radiation processing on icy materials under extremely cold conditions. This has direct relevance for understanding the composition and appearance of icy surfaces in exoplanetary systems. Are the icy moons and dwarf planets orbiting distant stars likely to be pristine and bright, or dark and covered in complex organics like Varuna? Varuna is a test case for the outcomes of space weathering in the deep freeze. The mystery of Varuna's potentially low density or unusual internal structure also speaks to the diversity of formation pathways. If it is indeed porous or less differentiated than expected, it challenges standard models of accretion and internal heating. This prompts us to consider if similar porous, low-density objects might be common outcomes of formation in other cold environments, perhaps representing an early stage of accretion that didn't proceed to full compaction and differentiation. Furthermore, Varuna's place within the Kuiper Belt structure and its enigmatic orbit contribute to our understanding of how giant planets influence the distribution of smaller bodies. As we detect exoplanets in other systems, particularly giant planets on wide orbits, understanding how our own giant planets shape the Kuiper Belt, using objects like Varuna as tracers, helps us predict the potential architecture and dynamics of debris disks and minor body populations in those distant systems. Varuna's history of potential scattering or resonance interactions provides vital data for testing models of planetary migration and gravitational sculpting. In essence, every unexplained mystery of Varuna is a question about the universe at large. This distant, enigmatic dwarf planet, a world of contradictions with its rapid spin and quiet interior, Its dark surface and bright spots, its expected ice and spectral silence, forces us to broaden our perspective and refine our theories. Varuna is a crucial piece of the cosmic puzzle, a reminder that even in the most familiar corners of the universe, there are worlds that operate according to rules we are only beginning to understand, offering profound insights into the processes that build and shape planetary systems across the cosmos. Unlocking the secrets of Varuna isn't just about understanding one distant world. It's about understanding the universe itself, one mystery at a time. As we consider Varuna's place within the grand architecture of the Kuiper Belt, another profound puzzle emerges: its remarkable loneliness. When we plot the locations of the largest, most massive objects in the Kuiper Belt outside of the resonant populations, they tend to be somewhat clustered or at least not completely isolated. You find groups of objects within certain orbital ranges, perhaps hinting at formation locations or shared histories, but Varuna seems to stand apart. It's a significant object, one of the largest known KBOs outside of the official dwarf planets and resonant objects, yet it lacks close neighbors of comparable size. It orbits in a region that isn't densely populated with other large bodies, appearing almost solitary in the vastness of the outer solar system. Why is Varuna so alone among its large KBO peers? One compelling explanation involves the process of dynamical clearing. While Varuna hasn't cleared its orbital neighborhood in the way a planet does, the gravitational influence of larger bodies, or even cumulative interactions over cosmic timescales with a greater number of smaller objects, could have gravitationally perturbed the orbits of many other large objects that might have initially formed nearby. Imagine Varuna as a ship sailing through a region where other large ships once sailed, but those others have since been pushed onto different routes or even out of the area entirely by distant gravitational currents or close encounters. Over billions of years, even relatively weak gravitational interactions can accumulate, slowly altering orbits and scattering objects from their original formation locations. Perhaps Varuna's specific orbital path, its slight eccentricity and inclination, placed it in a region that was dynamically cleared of other large objects by interactions with the giant planets during their migration, or by gravitational stirring within the Kuiper Belt itself. It's possible that other comparably sized objects did form in Varuna's vicinity, but they were subsequently scattered into different parts of the Kuiper Belt, the scattered disk, or even out of the solar system entirely, leaving Varuna as a solitary survivor in that particular orbital zone. Its current location might be a relatively stable pocket in a region that was otherwise swept clean of larger bodies. Another intriguing possibility is that Varuna's apparent loneliness is a clue to its rare formation conditions. Perhaps the specific circumstances required to form an object as large as Varuna in that particular region of the early solar nebula were unusual. The amount of solid material available, the local temperature and pressure conditions, or the velocity distribution of the accreting particles might have been just right to form one substantial object or a system that resulted in one large object, but not conducive to forming multiple large bodies nearby. Think of it like finding one very large diamond in a mine where most diamonds are smaller. The conditions for forming that single large one might have been unique to its specific location. If the amount of solid material in Varuna's formation zone was somehow limited, or if the accretion process was particularly efficient at consolidating the available material into a single body rather than distributing it among multiple large objects, that could explain its relative isolation. This would imply that the distribution of material in the early Kuiper Belt wasn't perfectly uniform, with some regions being richer in planetesimal building material than others. The loneliness of Varuna is also subtly linked to the discussion of its missing collisional family. If a major impact shattered a larger body to form Varuna, and the debris was scattered widely, it's conceivable that the parent body itself was already relatively isolated, or that the impact was so energetic that it cleared out much of the surrounding large material in addition to scattering the fragments. This scenario combines the idea of a major event with the concept of dynamical clearing, suggesting that both the impact and subsequent gravitational interactions played a role in leaving Varuna relatively alone. Understanding Varuna's isolation requires analyzing its orbital dynamics in the context of the entire Kuiper Belt population. By simulating the gravitational interactions between objects over billions of years, scientists can try to determine if Varuna's current position is a likely outcome of standard evolutionary processes acting on an initially more crowded region, or if it points to a truly unique history or formation environment. Its lonely orbit is a silent testament to the dynamic and often violent history of the outer solar system, suggesting that even large objects are not immune to being sculpted and scattered by the relentless forces of gravity, leaving some, like Varuna, to orbit in relative solitude, a significant world without the company of comparable peers. Given its unusual density estimates, we're led to mystery number 26, the debate swirling around Varuna's hidden internal structure. Is this distant dwarf planet a uniform blend of rock and ice throughout, or is it differentiated, meaning the heavier rocky material has settled into a core with lighter ice forming an outer shell, similar to how Earth has a metallic core and a rocky mantle? This isn't just an academic question. The answer reveals fundamental truths about Varuna's thermal history and how it evolved internally since its formation billions of years ago. The primary clue we have about Varuna's internal structure, short of sending a mission there, comes from those puzzling density calculations we discussed earlier. Remember how Varuna's estimated density seemed lower than expected for a solid object of its size. That low density, if accurate, is a significant piece of evidence in favor of Varuna not being fully differentiated, or at least not having a large, dense rocky core. When a body differentiates, the denser materials, primarily rock and metal, sink to the center under the influence of gravity, while lighter materials like ice float to the surface. This process naturally leads to a higher average density for the core region and a layered structure overall. If Varuna has a surprisingly low overall density, it could mean that the rock and ice are still largely mixed together, like ingredients in a cake before baking, rather than being separated into distinct layers. This would point towards an undifferentiated or only partially differentiated internal structure. In this scenario, the rocky components, which are denser, might be distributed relatively evenly throughout the icy matrix, creating a uniform composition from the surface down towards the center. This kind of structure would be expected if Varuna never got warm enough internally for long enough for the rock and ice to separate effectively. The heat needed for differentiation typically comes from the energy released during accretion, when countless smaller particles collide and stick together to form a larger body, and from the decay of radioactive elements contained within the rocky material. If Varuna accreted relatively gently, or if its rocky component has a lower than average abundance of radioactive isotopes, it might not have generated or retained enough heat to trigger full-scale differentiation. However, there are arguments for at least partial differentiation. Even with a low overall density, if there's some internal heat, the densest materials will begin a slow creep towards the center over vast timescales. The fact that Varuna is a relatively large object means its self-gravity is significant, providing the driving force for this separation if conditions allow. Some scientists hypothesize that Varuna might be partially differentiated, with a small, primitive rocky core surrounded by a thick, icy mantle, but perhaps with significant porosity throughout the structure, which would keep the overall average density low. Imagine a collection of rocky pebbles embedded in a porous block of ice. The denser pebbles are there, but the overall density is reduced by the air or empty spaces within the ice. This porous, partially differentiated model attempts to reconcile the low density with the expectation that larger bodies should undergo some degree of internal processing. The rapid rotation of Varuna also adds a layer of complexity to the internal structure debate. While rapid spin can affect the shape of an object, creating an equatorial bulge, it doesn't directly cause differentiation. However, if a giant impact caused both the rapid spin and influenced the internal structure, perhaps that impact mixed up the materials internally or even created voids, contributing to a lower density or preventing full differentiation even if the initial components were capable of it. The way Varuna responds to internal stresses from its rapid spin could also provide subtle clues to its internal mass distribution, although detecting these effects from Earth is incredibly challenging. Ultimately, determining whether Varuna is differentiated or not is crucial for understanding its thermal history. An undifferentiated body suggests a colder, less active past internally, while a differentiated body implies it reached temperatures sufficient for melting or softening. The debate over Varuna's internal structure, fueled by its mysterious density, highlights how interconnected its properties are. Its low density is a key clue, but interpreting that clue requires considering how its formation, its potential impact history, and its composition all contributed to the distribution of rock and ice within this distant, enigmatic world. It leaves us wondering whether Varuna is a relatively unprocessed relic of the early solar system's building blocks, or if it underwent a unique, perhaps incomplete, process of internal transformation, adding another layer to the many secrets hidden beneath its dark, icy surface. Moving from the debate about its internal structure, we arrive at mystery number 27, a profound question about Varuna's very substance. Does it act as a cosmic time capsule, preserving pristine, unaltered material from the earliest days of the solar system? Or has it been significantly altered over billions of years, its original composition lost to processing and change? This is a critical question because much of our understanding of the materials that form the planets relies on studying objects like comets, asteroids, and Kuiper Belt objects, which are considered remnants of that primordial era. If Varuna is indeed a time capsule, its composition could provide invaluable insights into the chemistry of the solar nebula far from the Sun, telling us exactly what kind of dust, ice, and organic molecules were available in the frigid outer reaches 4.5 billion years ago. The argument for Varuna being a time capsule centers on its location and estimated low internal heating. Residing far out in the cold Kuiper Belt, it has experienced much lower temperatures throughout its history compared to objects closer to the Sun. This extreme cold means that many volatile compounds that would evaporate or undergo significant chemical changes closer in have likely remained frozen and relatively unaltered within Varuna. If Varuna's internal heating from radioactive decay was also relatively low, as suggested by its potentially undifferentiated structure and radio silence, then its interior might have remained cold and stagnant since formation, preserving a pristine sample of the materials from which it accreted. Imagine taking a deep core sample from Varuna. The hope is that the material brought up from beneath the surface would be identical to the dust and ice grains that first clumped together in the outer solar nebula, providing a direct window into cosmic history. Objects that are considered primordial time capsules are those that haven't experienced significant thermal processing, meaning they haven't been heated enough to melt, undergo widespread chemical reactions, or differentiate into distinct layers. They are essentially frozen in time, preserving the chemical and isotopic composition of the cloud they formed from. If Varuna fits this description, studying its bulk composition, if we could ever ascertain it, would be like reading the ingredients list for the outer solar system recipe. However, several of Varuna's other mysteries challenge the simple picture of it being a pristine time capsule, suggesting instead that it has been significantly altered. Its dark, reddish surface, attributed to radiation-processed organics tholins, is clear evidence of surface alteration. This outer layer is definitely not primordial. It's a product of billions of years of exposure to sunlight and cosmic rays. While this surface layer might be thin, it shows that at least the outermost parts of Varuna have been chemically transformed. Then there's the possibility of a giant impact. A collision powerful enough to cause Varuna's rapid spin and potentially fragment a larger body would have generated tremendous heat. This heat could have caused widespread melting, vaporization, and chemical reactions within the impacted object, fundamentally altering the composition and structure of the materials involved. If Varuna is a fragment of a larger body that underwent such a process, its current composition might be a product of that violent event, not representative of the original pristine material. Even without a catastrophic impact, if Varuna underwent partial differentiation, as some models suggest, that process would have involved internal heating and chemical separation, also altering the original material distribution. Objects that have undergone significant thermal alteration, whether from internal heating, impacts, or exposure to liquid water, lose their claim to being pristine time capsules. The original chemical signatures can be overwritten by the new conditions. For instance, if water ice melted and interacted with rocky material, it could create new minerals that weren't present in the primordial cloud. The debate is whether Varuna is like a layered object with a heavily processed surface and perhaps a tumultuous middle history related to impacts, but with a deep interior that does remain pristine, like a fossil embedded within altered rock. Or has the processing gone deep enough through impacts, internal heating, or other mechanisms that even the core is no longer truly representative of the solar nebula? The uncertainty surrounding Varuna's internal structure and thermal history is directly linked to this question of primality. A porous, undifferentiated interior might be more likely to preserve pristine material, while a denser, potentially differentiated core would suggest more internal processing. The lack of clear spectral ice signatures could also hint at altered materials, either due to tholin masking or chemical changes in the ice itself. Ultimately, determining whether Varuna is a cosmic time capsule or a processed remnant is one of its most profound mysteries. It influences how we interpret observations and how much weight we place on Varuna's composition as representative of the early solar system. Is it a sample of the original building blocks or a complex product of billions of years of evolution in the harsh environment of the outer solar system? Each possibility provides a different but equally valuable type of information about our cosmic origins. If it's pristine, it tells us about the starting conditions. If it's processed, it tells us about the processes that shape worlds over cosmic time. Varuna's nature as a potential time capsule, or lack thereof, is tangled up with all its other mysteries, making it a truly unique and challenging object to understand, but one with the potential to unlock fundamental truths about the history of our solar system and others. Moving from the profound question of whether Varuna is a time capsule, preserving the materials of creation, we stumble upon mystery number 28, a puzzle about something we should be detecting but aren't: the perplexing absence of expected interactions between Varuna and the solar wind. The solar wind is a constant stream of charged particles, mostly protons and electrons emitted by the sun, flowing outwards through the entire solar system. These particles carry their own magnetic field and interact with anything in their path that has a magnetic field or a conductive surface. Planets like Earth have strong magnetic fields that create a protective bubble, the magnetosphere, which deflects the solar wind. Objects without a global magnetic field, like the Moon or asteroids, still interact with the solar wind, and these interactions can leave detectable signatures, such as subtle changes in the solar wind itself as it flows around the object, or even secondary emissions produced when the charged particles hit the surface. For a body as large as Varuna, even without a strong intrinsic magnetic field, we would expect some level of interaction with the constant bombardment of solar wind particles, something that telescopes designed to detect radio waves or other forms of radiation might pick up. Yet, observations aimed at detecting these interactions around Varuna have come up empty-handed. There's no detectable bow shock, the wave created in the solar wind as it slams into a magnetosphere or a solid object, and no clear signs of radiation generated by particle bombardment of the surface. Varuna seems to be remarkably transparent or perhaps inert to the solar wind, allowing the stream of charged particles to flow past it with minimal disturbance. So, why this apparent lack of interaction? One possibility, as we discussed earlier in the context of Varuna's radio silence, is that Varuna simply lacks a significant intrinsic magnetic field. If there's no internal dynamo generating a global magnetic field, then there's no large-scale magnetosphere to push the solar wind away. This aligns with the idea of a cold, potentially undifferentiated interior, where the conditions for generating a magnetic field, a conductive fluid in motion, are not met. However, even objects without a global magnetic field still interact with the solar wind via their physical presence. The charged particles in the solar wind can be absorbed by or scattered off the surface, and this interaction can sometimes generate faint radio waves or other forms of radiation. The fact that we don't detect these suggests either very weak interactions or that any resulting emissions are below our current detection thresholds. Another factor could be the unique properties of Varuna's surface. The conductivity of the surface material plays a role in how it interacts with the charged particles of the solar wind. If Varuna's dark, tholin-rich surface layer has unusually low electrical conductivity, it might be less effective at interacting with the charged particles hitting it. Imagine trying to channel electricity through a poor insulator. The interaction is weak. A highly insulating surface could effectively shield the interior and minimize the electromagnetic interactions with the solar wind. Conversely, if there are localized patches of more conductive material, perhaps exposed ice or minerals, we might expect to see some localized interactions, but the overall lack of detectable interaction suggests that either the entire surface is poorly conductive, or any more conductive patches are too small or too limited to produce a detectable signal. Furthermore, the nature of the solar wind itself at Varuna's vast distance could play a role. While the solar wind extends throughout the solar system, its density and speed change with distance from the Sun. It's possible that at Varuna's location, the characteristics of the solar wind are such that its interaction with a body like Varuna produces weaker signals than we might expect based on observations closer to the Sun. However, even in the outer solar system, the solar wind is a significant force, and other objects in the Kuiper Belt are thought to interact with it. The mystery of Varuna's missing solar wind interactions is a piece of the puzzle that speaks to its electromagnetic properties and, indirectly, its internal structure and surface composition. It suggests a lack of a significant magnetic field, potentially a low conductivity surface, or perhaps weaker interactions than our models currently predict. It's a subtle anomaly detected not by seeing something present, but by failing to see something expected, forcing astronomers to consider why Varuna appears so electromagnetically quiet despite being constantly bathed in the solar wind. This silence is a clue, hinting at a unique combination of interior and surface properties that set Varuna apart, adding another layer to its enigmatic nature in the frigid outer reaches of the solar system. Moving from the mystery of its potential internal structure and whether it's a time capsule, we arrive at mystery number 29, a puzzle that has sparked considerable debate within the astronomical community, the Great Varuna controversy centered around its very classification. Is Varuna truly a dwarf planet, or does it sit in a more ambiguous category? This isn't just a matter of semantics. It touches on the ongoing scientific process of defining and categorizing the diverse objects we're discovering in the distant solar system, particularly as new information challenges old assumptions. The International Astronomical Union, or IAU, laid out the criteria for what constitutes a dwarf planet back in 2006, during the same lively debate that led to Pluto's reclassification. To be a dwarf planet, an object must orbit the Sun, not be a moon, have enough mass for its own gravity to pull it into a nearly round shape, a state called hydrostatic equilibrium, and not have cleared the neighborhood around its orbit of other smaller objects. Varuna easily meets the first two conditions, orbiting our Sun and not being a satellite of another body. It also clearly satisfies the fourth. It resides within the crowded Kuiper Belt, sharing its orbital space with countless other icy bodies, so it hasn't cleared its neighborhood. The heart of the Varuna controversy lies with that third criterion, having sufficient mass to be in hydrostatic equilibrium, meaning it's been rounded by its own gravity. This is where the uncertainties surrounding Varuna's size and density become critically important. As we discussed, estimating Varuna's diameter is challenging, with different methods yielding slightly different results, generally placing it between 8 and 900 kilometers across. For an icy rocky body, the threshold for achieving hydrostatic equilibrium, the point at which gravity overwhelms the strength of the material and pulls it into a rounded shape, is estimated to be somewhere between 400 and 1,000 kilometers in diameter. The exact size required depends on the object's composition and whether it contains materials like ice that soften and deform more easily than rock. Given Varuna's estimated size range, it falls squarely within the zone where objects are expected to be rounded by their own gravity. Most dwarf planets confirmed or considered likely candidates are within or exceed this size. Therefore, based on its size alone, Varuna appears to meet the hydrostatic equilibrium requirement. However, the controversy isn't settled just by looking at the size range. Varuna's rapid rotation poses a significant challenge to the simple idea of hydrostatic equilibrium. An object spinning as fast as Varuna does experiences strong centrifugal forces, particularly at its equator. These forces counteract gravity and can cause the object to bulge significantly around its middle, becoming noticeably non-spherical, even if it has enough mass to be round if it were spinning slower or not at all. Think again of that rapidly spinning ball of dough flattening out. If Varuna's estimated non-spherical shape, driven by its spin, is substantial, it raises the question: does an object in hydrostatic equilibrium necessarily have to be currently perfectly rounded, or does the definition allow for deviations caused by rotation? Different scientists have different interpretations. Some argue that if the underlying mass is sufficient to tend towards roundness, even if the rapid spin distorts the shape, it still qualifies. Others believe that the observed shape must be consistent with hydrostatic equilibrium at that rotation rate, and if the distortion is too great compared to models of a fluid body spinning at Varuna's speed, it might not technically meet the definition. If Varuna is significantly elongated or flattened beyond what our models predict for a tidally relaxed, rapidly rotating body of its size and inferred composition, it strengthens the argument against it being in hydrostatic equilibrium. Furthermore, the potential for Varuna to be a fragment of a larger body from a massive impact adds another layer of complexity. If Varuna is essentially a large, irregular piece that broke off a parent body, its shape might be a remnant of that violent event rather than a shape achieved through gravity pulling material into equilibrium. While gravity would gradually try to reshape the fragment over billions of years, a large, irregular piece might take an incredibly long time to become fully rounded, especially in the cold, solid state of the outer solar system. This scenario suggests its current shape might not be one of hydrostatic equilibrium, but rather a transient form slowly evolving. The debate over Varuna's classification is a microcosm of the larger challenge of applying strict definitions to the messy reality of cosmic objects. The IAU criteria were designed to bring order to a rapidly expanding list of discoveries in the Kuiper Belt, but objects like Varuna, with their unique and puzzling combinations of properties, continue to push the boundaries of those definitions. Currently, Varuna is generally listed as a dwarf planet candidate, or likely dwarf planet, by organizations like the Minor Planet Center, acknowledging its significant size while also implicitly recognizing that its status isn't as definitively settled as, say, Pluto or Eris. The uncertainty surrounding its precise size, density, and most critically, its true shape under the influence of its extreme spin, keeps the scientific discussion alive. Resolving this controversy will require more precise measurements of Varuna's physical parameters and perhaps a refinement of the definition of hydrostatic equilibrium as it applies to these cold, rapidly rotating worlds. Until then, Varuna remains in a state of classification limbo, a significant object whose very identity is entangled in the ongoing process of exploring and defining the diverse population of the distant Kuiper Belt. Beyond its current mysteries, Varuna holds one final, profound secret, the enigma of its ultimate fate. What does the future hold for this distant, solitary dwarf planet over the immense timescales of solar system evolution? While its current orbit appears relatively stable within the Kuiper Belt, the gravitational dance of the outer solar system is a slow, relentless process, and the long-term trajectory of any object within it is never entirely certain. Over millions and billions of years, even subtle gravitational nudges from the giant planets or close encounters with other KBOs or rogue objects can accumulate, gradually altering an object's path in ways that can dramatically change its destiny. Will Varuna continue to orbit the Sun in the Kuiper Belt indefinitely, a permanent resident of this frigid realm, or is it destined for a different, perhaps more dramatic conclusion? One compelling possibility for Varuna's ultimate fate involves its eventual ejection from the solar system entirely, sent hurtling into the vast emptiness of interstellar space. This scenario is often the destiny of objects whose orbits become highly perturbed by close gravitational encounters, particularly with the giant planets. If Varuna's orbit were to become more eccentric, bringing it closer to Neptune's path, a close pass could provide a gravitational slingshot effect, accelerating Varuna to a velocity high enough to escape the Sun's gravitational pull altogether. This is similar to how we use planetary gravity assists to send spacecraft to the outer solar system or even out of the solar system, but in Varuna's case, it would be a natural, potentially chaotic interaction. The outer regions of the solar system are a gravitational minefield on cosmic timescales, and objects with even slightly unstable orbits can be kicked out over time. Varuna's current orbit, while not in a strong, stable resonance like Pluto's, does have a noticeable eccentricity and inclination, making it potentially susceptible to such scattering events over very long periods. Scientists use complex computer simulations running forward billions of years to model these gravitational interactions and estimate the likelihood of different outcomes for objects like Varuna. These simulations suggest that a significant fraction of objects initially in the Kuiper Belt will eventually be ejected from the solar system due to gravitational interactions, becoming free-floating interstellar objects. Varuna, with its current orbital characteristics, fits the profile of an object that could eventually meet this fate. Another potential outcome, though perhaps less common for an object of Varuna's size and current location, is that its orbit could evolve inwards, sending it on a trajectory that brings it closer to the Sun. This is how many comets are thought to originate. Icy bodies from the Kuiper Belt or the more distant Oort cloud are perturbed into orbits that plunge them into the inner solar system. If Varuna were somehow nudged onto such an inward path, it would become a spectacular, although probably singular, visitor to the inner solar system, developing a massive coma and tail as its abundant ices sublimated in the Sun's increasing heat. While its size might make it less susceptible to the multiple scattering events that typically send smaller comets inwards, it's not impossible on cosmic timescales. An inward trajectory could also potentially lead to a collision with one of the inner planets or the Sun itself, although such outcomes are statistically very rare. A third possibility, though perhaps less of an ultimate fate and more of a significant interim event, is that Varuna could experience a close encounter or even a collision with another substantial object in the Kuiper Belt in the distant future. While the major collisions that likely shaped its past are thought to have occurred early in solar system history when the Kuiper Belt was more crowded and dynamically active, the region still contains many objects. Over millions of years, the cumulative effect of orbital evolution and minor perturbations could bring Varuna into the path of another large KBO, leading to another significant impact. The outcome of such a collision would depend on the size and speed of the colliding objects, but it could result in further fragmentation of Varuna, the creation of a new family of debris, or even the merger of the two objects into a larger body. There is also the possibility that Varuna's orbit might evolve into a more stable configuration over time, perhaps settling into a weak resonance with Neptune or another giant planet that offers some protection from future scattering events. The orbital landscape of the Kuiper Belt is complex, with hidden pockets of stability and instability that objects can drift into or out of over eons. Varuna's long-term survival in its current state depends on whether its current orbital path is truly stable against the cumulative effects of gravitational perturbations over the remaining lifespan of the solar system. Projecting the future trajectory of any distant object over billions of years is inherently uncertain, relying heavily on the accuracy of our models and our knowledge of the current state of the solar system. Subtle, presently undetectable gravitational influences could play a significant role in Varuna's very distant future. However, by studying its current orbit and properties, scientists can estimate the probabilities of these different outcomes. The mystery of Varuna's ultimate fate is a reminder that the solar system is not a static place, but a dynamic system constantly evolving over immense timescales. This distant, enigmatic dwarf planet, with all its unexplained mysteries, is not just a relic of the past or a puzzle of the present. It is an object with a future trajectory that is still being written in the silent, gravitational language of the cosmos, a destiny that could involve continued quiet orbital motion, a violent collision, or a lonely journey into the interstellar void. This final mystery leaves us pondering the long, uncertain road ahead for Varuna, a world that continues to challenge our understanding from its distant, shadowed corner of the solar system. So, we've journeyed through 30 layers of mystery surrounding the distant dwarf planet Varuna, a world that consistently defies our expectations and challenges the very foundations of planetary science. We've seen how its incredibly rapid spin, whipping around in just over 3 hours, flies in the face of what we expect for objects of its size in the Kuiper Belt, hinting at a violent past shaped by massive impacts or unusual formation processes. We've grappled with the enigma of its dark, reddish surface and unexpectedly low reflectivity, a cosmic canvas that seems to be dominated by mysterious organic compounds or heavily processed ice, raising questions about its composition and the effects of billions of years of radiation exposure. We've pondered the puzzling absence of a detectable atmosphere and orbiting moons, suggesting either a fundamental difference in its volatile content compared to neighbors like Pluto, or a history so turbulent that any potential satellites were lost to the void. Its cryptic spectral signatures, failing to show clear evidence of common ices like water and methane, leave us wondering what exotic materials might be hidden on its surface, pushing the limits of our understanding of chemistry in the outer solar system. We've explored the conflicting estimates of its size and density, forcing us to confront the uncertainties in our methods and hinting at a potentially porous or undifferentiated interior that doesn't fit neatly into standard models of internal structure. We've seen how its slightly eccentric and inclined orbit, its possible non-spherical shape, and the strange behavior of its light curve over time all point towards a dynamic history, perhaps shaped by giant impacts, planetary migration, or ongoing evolutionary processes far from the Sun's influence. The lack of a detectable collisional family around it, when combined with evidence suggesting a violent past, highlights the sheer scale and complexity of events that could have scattered debris far and wide. Even its apparent radio silence and lack of interaction with the solar wind pose riddles about its electromagnetic properties and internal state. And perhaps most fundamentally, Varuna challenges our very models of how cold, icy worlds form and evolve, sitting awkwardly within the classification system, a true outlier whose collection of anomalies demands new theories and deeper investigation. Every single one of these 30 mysteries is more than just an isolated puzzle. They are interconnected pieces of a larger, more complex picture that forces us to reconsider our assumptions about the outer solar system. Varuna isn't just another data point, it's a crucial test case for our understanding of planet formation, orbital dynamics, surface chemistry, and internal structure in the coldest reaches of our cosmic neighborhood. It highlights the incredible diversity of objects that were born from the same primordial cloud of gas and dust, yet have followed dramatically different evolutionary paths over billions of years. It reminds us that the Kuiper Belt, far from being a static graveyard of icy remnants, is a dynamic and mysterious region where unexpected processes might still be at play. Varuna stands as a testament to the limits of our current knowledge and the vastness of what we have yet to discover. It pushes the boundaries of observational astronomy, requiring ever more powerful telescopes and sophisticated techniques to capture its faint light and decipher its secrets. It inspires new theoretical models, prompting scientists to explore scenarios involving hyper-energetic impacts, unusual compositions, and unique formation conditions. The story of Varuna is still being written, observation by observation, theory by theory. But here's where you, the curious stargazer, the backyard astronomer, can potentially play a role in helping unravel some of these puzzles. While professional observatories conduct the most detailed studies, Varuna is sometimes visible even through moderate amateur telescopes during periods of opposition. Opposition is when an outer planet or dwarf planet is on the opposite side of the Earth from the Sun, making it appear brightest and largest in the night sky. While Varuna will still be a faint point of light, tracking its position over time, carefully estimating its brightness relative to nearby stars, or even attempting to capture images can contribute to the ongoing scientific effort. Long-term amateur observations, carefully documented and shared, can provide valuable data points on Varuna's changing brightness, potentially helping to confirm or refute observations of its varying light curve, or even subtly refine its orbital path. Citizen science projects sometimes emerge that allow enthusiasts to contribute to the analysis of astronomical data. So keep an eye on astronomical news for Varuna's oppositions. Learn how to locate it in the night sky. With patience and persistence, you too can connect with this distant, mysterious world, participating in the grand human endeavor to map and understand the cosmos. Varuna is out there, a beacon of mystery in the frigid darkness, waiting for its secrets to be uncovered, and every pair of eyes turned skyward is a step closer to solving its 30 profound enigmas. The journey to understand Varuna is ongoing, and it's a journey for all who are captivated by the unexplained wonders of the universe.